We have never seen our own home from above. Not really, not the way you might imagine. We have photographed galaxies 13 billion light-years away. We have sent probes to the edge of interstellar space, beyond the grip of the sun's influence, traveling for decades into the cold and the dark. We have mapped the surface of Pluto, landed on a comet, and captured the light of stars that died before Earth had bones. But there is one photograph that does not exist, one view that has never been captured. A simple image looking down at our solar system from 90 degrees above the sun, a family portrait taken from the one direction humanity has never been able to reach. It is not a matter of distance, it is a matter of direction. And direction in space is harder than you think. Every spacecraft we have ever launched, every probe, every satellite, every astronaut who has ever left the surface of this planet has remained trapped inside an invisible prison, a flat disk of gravitational efficiency we call the ecliptic plane. It is where the planets live. It is where the energy is cheapest. And it is the reason we have spent 70 years exploring the cosmos in 2 dimensions, like creatures born into a world with no concept of up. Only one probe has ever tried to escape. Its name was Ulysses. It climbed to 80 degrees, high enough to glimpse the poles of the sun, but not high enough to see the system laid bare beneath it. And then it ran out of fuel, and the mission ended, and no one has tried again. So why are we trapped in the disk? What would it take to break free? And what might we see if we ever managed to look straight down at the sun and everything that orbits it, from a place no human-made object has ever been? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. We live in a flatland and we don't even realize it. Right now, as you sit wherever you are, Earth is tracing a path around the sun. A smooth ellipse, nearly circular, tilted at no particular angle to anything except itself. That path, extended outward in every direction as an imaginary surface cutting through space, is called the ecliptic plane. And for reasons that made perfect sense at the time, but have quietly locked humanity into a single narrow view of the cosmos, almost everything we have ever launched into space stays inside it, not near it, inside it, hugging it like a car that refuses to leave the highway. Every planet in the solar system orbits in roughly the same flat disk. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. All of them circle the sun along paths that tilt no more than a few degrees away from one another. If you could freeze the solar system in place and look at it edge on, you'd see a thin, bright line of worlds stretched across the black. No spheres of planets scattered in 3 dimensions, just a disk, a cosmic pancake with the sun glowing at the center and everything else spinning in lockstep around it. The ecliptic is not a real object, it's a concept, a reference line astronomers invented to make sense of where things are in the sky. But like all good concepts, it describes something physical underneath. The solar system formed from a collapsing cloud of gas and dust about 4.5 billion years ago. As that cloud collapsed, it started spinning, and as it spun, it flattened. Picture a pizza chef tossing dough into the air. Gravity pulled inward, rotation spread outward. The result was a disk. The sun ignited at the center. The planets condensed from the leftover material in the disk around it. And because they all formed in the same flat structure, they all ended up orbiting in more or less the same plane. There's nothing special about the ecliptic's orientation in space. It's not aligned with the plane of the Milky Way. It's not pointing at anything in particular. It's just the random angle at which that original cloud happened to be spinning when it collapsed. If the cloud had been rotating on a different axis, the ecliptic would sit somewhere else in the sky, and we'd call that the reference plane instead. The universe doesn't care. The ecliptic is a human convenience, a coordinate system we invented because the objects we care about all happen to live there. From Earth, the ecliptic appears as a line across the sky. The sun moves along it over the course of a year. The moon crosses it every month, wobbling slightly above and below by about 5 degrees. The planets wander along it at their own speeds, which is why ancient astronomers called them wanderers in the first place. If you go outside tonight and trace a line from where the sun set through the brightest planets visible after dark, you're drawing the ecliptic. It's always there, a faint, invisible highway running through the constellations of the zodiac. And here's the thing, when humanity started launching spacecraft, we kept launching them into that same flat plane, not because we were unimaginative, because it was by far the most efficient thing to do. Rockets are expensive. Fuel is heavy. Every kilogram you carry into space costs thousands of dollars, and every meter per second of velocity you need to add or subtract costs exponentially more in propellant. If you want to send a probe to Mars, and Mars is already orbiting in nearly the same plane as Earth, the smart move is to launch into that plane and let the natural orbital mechanics do most of the work. You're already moving at 30 kilometers per second just by standing on Earth's surface as it circles the sun. That's free velocity. Use it. If you want to visit Jupiter, same story. Jupiter sits just over 1 degree away from the ecliptic. You launch into the ecliptic, coast outward, and let Jupiter's gravity bend your trajectory when you arrive. Clean, efficient, reliable. If you want to visit Saturn, Uranus, Neptune, any of the moons, any of the asteroids, almost any destination in the solar system, the math says stay in the plane. The targets are already there. The shortest path between 2 points is the one that doesn't waste fuel fighting gravity to climb out of the disk. So we didn't. We stayed in the disk, and we're still there. Every Mars rover, every Jupiter probe, every Saturn orbiter, every flyby mission to the outer planets, every asteroid rendezvous, every comet intercept, all of them launched into or very close to the ecliptic plane. Even the Voyager probes, which flew farther than anything else humanity has ever built, spent the majority of their journey inside the plane. Voyager 1 eventually tilted upward after its encounter with Saturn, climbing at an angle of about 35 degrees relative to the ecliptic. Voyager 2 dipped downward after Neptune, descending at about 48 degrees below. But those tilts didn't happen by choice. They happened because the probes used gravity assists from the giant planets to pick up speed, and the geometry of those flybys determined the angles they were flung outward at. The spacecraft didn't steer out of the plane, they were kicked. For decades, this wasn't a limitation anyone worried about. The ecliptic is where the planets are. The planets are what we wanted to study. Mission accomplished. But the result is that humanity has spent 70 years building a map of the solar system from inside a single narrow band. Imagine you live your entire life on a flat plane, no hills, no mountains, no valleys, just horizon in every direction. You'd learn a lot about planes. You'd get very good at navigating flat terrain. But you'd never see what the landscape looks like from above. You wouldn't know if there were rivers just over the horizon or forests or deserts. You'd be missing context. That's where we are. We've been living in a cosmic flatland, looking outward along the ecliptic, observing everything in profile. The sun appears as a disk because we only ever see it from the side. The planets appear as dots moving along a line because that's the only angle we've ever looked at them from. The solar wind, the magnetic field, the structure of interplanetary space, all of it has been measured from within the plane. We're drawing conclusions about a three-dimensional system using data collected from a two-dimensional slice. It's not that the data is wrong, it's that it's incomplete. And the thing about incomplete data is that you don't always know what you're missing until you step outside the frame and look back. There are directions in space we have barely touched: straight up, straight down, 90 degrees above the sun's north pole, 90 degrees below the south pole. Those directions are not unreachable. They're not blocked by some physical barrier. They're just expensive. Tilting a spacecraft's orbit out of the ecliptic costs velocity, a lot of it, and velocity costs fuel, and fuel costs money, and money in space exploration is always in short supply, so those directions remain mostly unexplored. Not forbidden in the sense that we can't go there. Forbidden in the sense that we haven't been willing to pay the cost. The Moon's orbit offers a clue to how narrow our perspective really is. The Moon doesn't orbit Earth along the ecliptic. Its orbital plane is tilted about 5.1 degrees away from it. That's a tiny tilt, barely noticeable, but it's enough that the Moon spends part of each month above the ecliptic and part of it below. When the Moon crosses the ecliptic at the same moment it passes between Earth and the Sun, we get a solar eclipse. When it crosses while on the opposite side of Earth from the Sun, we get a lunar eclipse. Those crossing points are called nodes, and eclipses only happen when the alignment is exact. The Moon's 5-degree tilt is one of the reasons we don't get eclipses every month. Most of the time, the Moon passes slightly above or slightly below the Sun from our perspective. The shadow misses. The alignment has to be just right. If the Moon orbited exactly in the ecliptic with zero tilt, we'd get a solar eclipse every single month and a lunar eclipse 2 weeks later. The sky would be a clockwork of shadows. That 5-degree wobble is nothing. 5 degrees off the ecliptic is still basically in the ecliptic. You'd never notice it unless you were tracking the Moon's position carefully over time. But it's a reminder that even the most familiar object in our sky doesn't sit perfectly flat. There's always a little tilt, a little deviation. The universe has 3 dimensions. The ecliptic is just the dimension we happen to occupy. From inside the plane, the solar system looks orderly. The planets line up. They move in predictable paths. You can draw diagrams on a flat sheet of paper, and they make sense. Teachers do this all the time. Textbooks do this. Every illustration of the solar system you've ever seen in school showed the planets strung out in a line or arranged in concentric circles around the Sun, all in the same flat plane. It's visually clean, it's easy to understand, and it's deeply misleading because the solar system isn't flat, it's a sphere. The Sun doesn't just shine outward along the ecliptic, it radiates in every direction. The solar wind doesn't just blow along the plane, it expands outward in a bubble, a sphere of charged particles pushing against the interstellar medium in all directions at once. The Sun's magnetic field doesn't lie flat, it twists and stretches and loops, filling space in 3 dimensions. The solar system is not a disk, it's a ball, and we've only ever studied it from the equator. What does the solar system look like from above? What does the Sun's north pole look like when you're hovering directly over it, looking straight down? What does the heliosphere, that vast bubble of solar wind, look like when you're outside the plane, watching it from an angle we've never seen? We don't know. We have simulations, we have models. Scientists have run the math and drawn pictures of what they think it should look like, but we've never pointed a camera at it. We've never sent an instrument package 90 degrees above the ecliptic to measure what's actually there. This isn't a small gap in our knowledge, it's a foundational one. The Sun is the single most important object in the solar system. It's the source of almost all the energy that powers everything we see. It's the anchor that holds the planets in orbit. It's the engine that drives space weather, solar flares, coronal mass ejections, the whole chaotic dance of plasma and magnetic fields that fills the space between worlds. And we've never seen it whole. We've looked at the sun from Earth. We've sent spacecraft to study it up close. The Parker Solar Probe is currently diving closer to the sun than any object humanity has ever built, skimming through the corona at distances that would vaporize anything not wrapped in a heat shield. But Parker is still moving along the ecliptic. It's looking at the sun's equator, the same band we've always looked at. The poles remain out of reach. The European Space Agency launched a mission called Solar Orbiter in 2020 with the explicit goal of climbing out of the ecliptic. Over the course of its mission, Solar Orbiter will use repeated gravity assists from Venus to tilt its orbit gradually upward, reaching an inclination of about 33 degrees by the end of its nominal mission. If the spacecraft survives long enough, future mission extensions could push it even higher. 33 degrees is not 90. It's not even halfway to 90, but it's more than we've ever achieved before. And the images Solar Orbiter has sent back from even that modest tilt have already revealed structures in the sun's atmosphere that weren't visible from the ecliptic. 33 degrees was enough to show us we were missing things. Imagine what 90 would reveal. The problem is that getting to 90 degrees above the ecliptic is one of the hardest things you can do in orbital mechanics without leaving the solar system entirely. You can't just point a rocket upward and burn. Well, you can, but the amount of fuel you'd need is absurd. Every degree of inclination change costs velocity, and the cost scales exponentially the faster you're already moving. Earth is moving at 30 kilometers per second around the sun. To tilt your orbit 90 degrees out of the ecliptic while staying at roughly the same distance from the sun, you'd need to shed almost all of that sideways velocity and rebuild it in a perpendicular direction. The numbers don't work. No chemical rocket we've ever built could carry enough fuel to do it. So you cheat. You use gravity. You fly past a planet, let its gravity bend your trajectory, and steal a little bit of its orbital momentum in the process. Do it right, and you can change your inclination for free, or at least much cheaper than burning fuel. The problem is that the planets themselves are all in the ecliptic. If you want to tilt out of the plane, you need to approach a planet from just the right angle, thread a very precise trajectory past it, and hope the geometry works out. Most of the time, it doesn't. The planets aren't positioned conveniently for the kind of inclination changes we'd need. They're moving in the same flat disk, which means their gravity naturally pulls you back into the disk rather than kicking you out of it. Jupiter is the exception. Jupiter is so massive that its gravity can do almost anything if you're willing to get close enough. A single flyby of Jupiter can add or subtract kilometers per second of velocity in almost any direction you want, depending on how you approach. That's why Voyager worked. That's why so many missions to the outer solar system use Jupiter as a stepping stone. The planet is a shortcut, a gravitational bank account humanity can draw from anytime we need to go somewhere unusual. But even Jupiter has limits. The geometry has to line up. The planet has to be in the right position in its orbit at the right time. Launch windows for gravity assists are narrow, and they don't come around often. If you miss one, you might wait a decade for the next. There's one other option. Don't stay in the solar system. Leave it entirely. Coast out past the orbit of Neptune where the sun's gravity weakens, then curve your trajectory upward or downward and coast back in from above or below. That's called a Hohmann transfer, with an inclination change at aphelion, and it's theoretically possible. It's also slow. Depending on how far out you go, the trip could take decades just to reach the turnaround point, and decades more to come back. You'd be launching a mission your grandchildren might see the results of. Nobody has done it. Nobody has seriously proposed it. The engineering challenges alone would be staggering, and the scientific return would have to justify a mission timeline measured in generations. So far, it hasn't. What we're left with is a blind spot, a missing angle, a photograph we've never taken. Stand on the surface of Earth and look up. You can see the stars, the planets, the moon, the sun when it's daytime. You can see the ecliptic traced across the sky as a faint band of zodiac constellations. You're looking outward along the plane, the same way we've always looked. Now imagine tilting your perspective 90 degrees. Imagine rising straight up out of the solar system, climbing higher and higher until the ecliptic appears edge-on below you. The planets shrink into a thin, bright line. The sun sits at the center, a glowing sphere instead of a disk. The heliosphere stretches outward in all directions, a bubble of solar wind pushing into the dark, and above the sun's north pole there's a view no human eye, no human instrument has ever captured. We don't know what we're missing. That's the uncomfortable part. We can guess, we can model, we can simulate the physics and render it in software and convince ourselves we understand what's happening. But understanding a thing from inside the plane is not the same as seeing it from outside. The ecliptic has been good to us. It's where the worlds are. It's where the missions go. It's efficient, it's predictable, and it's gotten us farther than anyone in the 1960s thought possible. But it's also a cage, a comfortable one. A cage we built ourselves out of economics and orbital mechanics and the simple fact that the targets we cared about were all in the same place. And for a long time, that was fine. But the longer we stay inside the Flatland, the more we start to wonder what the rest of the map looks like. What's above? What's below? What have we been flying past for 70 years without ever looking up? There was one spacecraft that tried, just one. A probe that climbed higher out of the ecliptic than anything before or since, reaching an inclination of 80 degrees above the plane and looking down at the sun from an angle no other instrument has ever matched. Its name was Ulysses. There was one spacecraft that tried, just one. A probe that climbed higher out of the ecliptic than anything before or since, reaching an inclination of 80 degrees above the plane and looking down at the sun from an angle no other instrument has ever matched. Its name was Ulysses, and it got there by doing something no mission had ever attempted before. It threw itself at Jupiter, used the planet's gravity like a slingshot, and flung itself out of the Flatland entirely. The mission was born out of frustration. By the late 1970s, solar physicists had assembled a fairly detailed picture of the sun's equator. Spacecraft had been studying the solar wind, the constant stream of charged particles blowing outward from the sun's surface, for nearly 2 decades. Instruments on Earth and in orbit had measured the magnetic field, tracked sunspots, observed solar flares. The data was good, the models were getting better, but every single measurement had been taken from inside the ecliptic plane. The sun's poles, the regions directly above and below the solar equator, remained completely unexplored, not because they were uninteresting, because no one had figured out how to get there. The sun is not a simple object. It's a rotating ball of plasma with a magnetic field that flips polarity every 11 years. That field doesn't sit still. It twists, stretches, and loops, forming structures that arc thousands of kilometers above the surface before collapsing back down. Near the equator, the magnetic field is chaotic, tangled by the sun's rotation into a mess of loops and streamers. But at the poles, the field was predicted to be simpler, more organized, maybe even stronger. Nobody knew for sure. The models said one thing. The physicists wanted to check. The problem was velocity. If you want to tilt a spacecraft's orbit out of the ecliptic while staying at roughly the same distance from the Sun, you need to change direction without losing speed. That requires an enormous amount of energy. A spacecraft orbiting the Sun at Earth's distance is already moving at about 30 kilometers per second. To tilt that orbit by 90 degrees perpendicular to the ecliptic, you'd need to cancel out almost all of that sideways motion and rebuild it, pointing in a completely different direction. The math says you'd need a change in velocity of something close to 42 kilometers per second. That's absurd. The Space Shuttle, one of the most powerful launch systems ever built, could barely put 10 kilometers per second of velocity into a payload. A direct launch to a polar solar orbit was, in the language of mission planners, not feasible. It still isn't. So in the early 1980s, a group of engineers at the European Space Agency and NASA started sketching out a different plan. If you can't get there by burning fuel, you steal the velocity from somewhere else. You use gravity. Specifically, you use Jupiter. Jupiter is the largest planet in the solar system by a wide margin. It weighs more than twice as much as all the other planets combined. When a spacecraft flies past Jupiter, the planet's gravity pulls on it, bending its trajectory. If you approach from the right angle, you can use that gravitational pull to whip the spacecraft around the planet and send it flying off in a completely different direction at a completely different speed. The spacecraft doesn't carry extra fuel. It doesn't burn its engines. It just falls past Jupiter and gets flung out the other side like a stone from a sling. Physicists call this a gravity assist. Mission planners call it a slingshot. And it's one of the only ways to reach the kind of extreme orbits that chemical rockets can't touch. The trajectory they designed for Ulysses was elegant in the way good physics problems are elegant. Launch from Earth, coast outward toward Jupiter, arrive at Jupiter about a year and a half later, fly extremely close to the planet, threading a path just above the cloud tops where the gravity is strongest. Let Jupiter's gravity grab the spacecraft and rotate its velocity vector by about 80 degrees out of the ecliptic, then coast away from Jupiter on a long elliptical orbit that carries the spacecraft up and over the Sun's North Pole, back down under the South Pole, and around again. Repeat indefinitely. No fuel required after the initial launch except for tiny course corrections. On paper, it looked simple. In practice, it required hitting a target the size of a small country from a distance of 500 million kilometers while traveling at tens of thousands of kilometers per hour. Miss by a few hundred kilometers and the trajectory doesn't tilt enough. Miss by a few thousand and you fly past Jupiter entirely and end up in the outer solar system with no way back. The margin for error was tight, but it was doable. Ulysses launched on October 6, 1990, from Kennedy Space Center in Florida aboard the Space Shuttle Discovery. The shuttle carried it into low Earth orbit, then released it. A solid rocket booster called an inertial upper stage ignited and kicked the spacecraft out of Earth's gravity well, sending it on a long, curving path toward Jupiter. The probe itself was small by spacecraft standards, about the size of a compact car, weighing roughly 370 kilograms. It carried a suite of instruments designed to measure the solar wind, magnetic fields, cosmic rays, and radio emissions. It also carried a radioactive power source, a radioisotope thermoelectric generator, because solar panels wouldn't work. The trajectory to Jupiter and the orbit beyond would take Ulysses so far from the Sun that sunlight would be too weak to generate enough electricity. The spacecraft needed a battery that didn't depend on the Sun, so NASA gave it plutonium. The trip to Jupiter took 16 months. Ulysses coasted silently through the inner solar system, crossing the orbits of Mars and the asteroid belt, gradually picking up speed as the Sun's gravity pulled it inward and then flung it outward again in a carefully calculated arc. On February 8, 1992, it reached Jupiter. The flyby was almost absurdly close. Ulysses passed just 409,000 kilometers above Jupiter's cloud tops, well inside the orbit of Io, the innermost of the large Galilean moons. For reference, our own moon orbits Earth at an average distance of about 384,000 kilometers. Ulysses flew closer to Jupiter than the moon does to Earth. At that distance, Jupiter's gravity dominates everything. The spacecraft was moving at nearly 15 kilometers per second relative to the planet when it made its closest approach. Jupiter's gravity grabbed it, bent its trajectory by roughly 80 degrees, and hurled it upward out of the ecliptic like a pebble flicked off a spinning wheel. The maneuver worked. When Ulysses emerged from the other side of the flyby, its orbit had tilted. The spacecraft was no longer moving along the flat disk of the ecliptic. It was climbing. For the first time in the history of spaceflight, humanity had a probe on a trajectory that would carry it directly over the sun's poles. The orbit was an elongated ellipse. At its closest point, called perihelion, Ulysses swooped in to about 1.3 astronomical units from the Sun, just slightly farther out than Earth. At its farthest point, aphelion, it swung out to about 5.4 astronomical units, roughly the distance of Jupiter's orbit. The entire loop took about 6 years to complete. And because the orbit was tilted 80.2 degrees relative to the solar equator, each loop carried the spacecraft high above the Sun's North Pole, then down below the South Pole, giving it a vantage point no other mission had ever come close to. 80 degrees is not 90. It's close, but it's not the same. A true polar orbit would have taken Ulysses directly over the Sun's rotational axis, looking straight down at the pole from above. Instead, Ulysses passed overhead at an angle, viewing the pole from about 10 degrees off to the side. That's still an enormous improvement over the 0-degree inclination of every other solar mission, but it's worth understanding the difference. The spacecraft never hovered directly above the Sun's north or south pole. It never captured the perfect overhead photograph that would show the pole centered in the frame with the solar equator spread out in a perfect circle below. What it captured instead was an angled view, a perspective that revealed the polar regions but didn't quite frame them head-on. Why not go all the way to 90 degrees? The answer, once again, is velocity. The Jupiter flyby could only tilt the orbit so far. To reach a full 90-degree inclination, Ulysses would have needed to approach Jupiter from a slightly different angle, which would have required a different launch trajectory from Earth, which would have required more fuel than the mission had budget for. 80 degrees was the best compromise between what the physics allowed and what the engineering could deliver. And honestly, 80 degrees was extraordinary. No spacecraft before or since has come anywhere close. The first polar pass happened in 1994. Ulysses climbed up out of the ecliptic, crossed over the Sun's south pole in the summer of that year, and began sending back data. The instruments recorded the solar wind speed, density, and composition. They measured the magnetic field strength and direction. They tracked cosmic rays, high-energy particles from outside the solar system that were funneled toward the poles by the Sun's magnetic field. And almost immediately, the data started contradicting the models. The solar wind near the poles was faster than anyone predicted. Near the Sun's equator, the wind typically blows at about 400 kilometers per second. It's turbulent, gusty, full of variations. But over the poles, Ulysses measured wind speeds closer to 750 kilometers per second. Fast, smooth, and remarkably steady. The difference was so pronounced that scientists had to rethink how the solar wind was being accelerated away from the Sun. The equatorial wind, it turned out, was being slowed down by the tangled magnetic field near the Sun's equator. The polar wind, escaping from regions where the magnetic field was simpler and more open, could accelerate freely without running into obstacles. Then there was the magnetic field itself. Before Ulysses, most models assumed the Sun's magnetic field would be strongest at the poles, the way Earth's magnetic field is strongest near the north and south magnetic poles. That made intuitive sense. The poles are where the field lines converge, but Ulysses found the opposite. The Sun's polar magnetic field was weaker than expected, not stronger, much weaker, and it wasn't static. Over the course of the mission, as the Sun cycled through its 11-year activity period, the magnetic field at the poles didn't just weaken, it reversed. The North Magnetic Pole became the South Magnetic Pole, and vice versa. Ulysses watched it happen in real time, recording the slow collapse and reformation of the field over a span of years. That reversal was predicted. Solar physicists had known since the 1950s that the Sun's magnetic field flips polarity every 11 years, tied to the solar cycle of sunspot activity, but they'd never actually measured it at the poles. Ulysses gave them the first direct evidence that the reversal wasn't just happening at the equator, it was a whole Sun phenomenon. The field collapsed everywhere, restructured itself, and came back pointing the other way. Watching that process unfold from above the poles was like watching the Sun turn itself inside out. The mission also revealed something unexpected about how particles move through space. Before Ulysses, scientists assumed that charged particles, things like electrons and protons from solar flares or cosmic rays from distant supernovae, mostly followed the Sun's magnetic field lines. Those field lines are tied to the Sun's rotation, so they spiral outward in a pattern that keeps particles more or less locked to specific latitudes. If a particle starts near the Sun's equator, it stays near the equator. If it starts near a pole, it stays near the pole. That was the model. Ulysses found that particles don't obey the rules nearly as strictly as the models said they should. Energetic particles were showing up at high latitudes in much greater numbers than expected, suggesting they were moving across field lines much more easily than anyone thought. That has implications for space weather, for how solar storms propagate through the solar system, for how cosmic rays reach Earth. It means the heliosphere, that bubble of space dominated by the Sun's influence, is more connected than the old models allowed. A flare at the Sun's equator can send particles streaming toward the poles. A disturbance at one latitude can affect conditions everywhere. And then there was dust. Interstellar dust, tiny grains of solid material drifting through the galaxy. Some of it comes from dying stars, some of it comes from supernovae, some of it is just the accumulated debris of billions of years of cosmic activity. The solar system is constantly plowing through a cloud of this stuff as it orbits the center of the Milky Way. Scientists knew interstellar dust existed. They'd detected it in small amounts. But Ulysses found 30 times more of it than previous measurements had suggested. The dust was everywhere, streaming into the solar system, from the direction the Sun is moving through the galaxy, threading through the space between planets. Ulysses was the first spacecraft in a position to measure it properly because it was the first spacecraft outside the ecliptic plane where most of the solar system's native dust, the stuff left over from planet formation, is concentrated. From above and below the plane, the interstellar signal was clearer, and it was louder than anyone expected. Over the course of 17.5 years, Ulysses completed 3 full orbits. It passed over the Sun's South Pole in 1994, over the North Pole in 1995, then repeated the loop twice more, returning to the poles in 2000 and 2001, and again in 2007 and 2008. Each pass added more data, refining the picture of how the Sun's magnetic field and solar wind change over the course of the solar cycle. The mission watched the Sun at solar maximum, when sunspot activity peaks and the corona is full of streamers and loops, and at solar minimum, when the Sun quiets down and the corona looks smoother and simpler. The differences were stark. The solar wind at the poles during solar maximum was slower and more variable, closer to what you'd see at the equator. The magnetic field was messier, less organized. During solar minimum, the polar winds sped up again and the field lines straightened out. The Sun breathes. Ulysses measured the rhythm of that breathing from an angle no one else could see. The mission ended in June 2009, not because it ran out of things to measure, because it ran out of power. The radioisotope thermoelectric generator that had kept Ulysses alive for nearly 2 decades was slowly decaying. Plutonium-238 has a half-life of about 87 years, which sounds long, but the decay process generates heat, and that heat is what the generator converts into electricity. As the plutonium decayed, the heat output dropped. Less heat meant less electricity. By 2009, the spacecraft wasn't generating enough power to keep all its systems running. Engineers started shutting down instruments one by one to conserve what little power remained. They turned off heaters, they let parts of the spacecraft get cold, and eventually the fuel lines froze. Hydrazine, the propellant Ulysses used for attitude control, freezes at around 2 degrees Celsius. Once the lines froze, the spacecraft couldn't point its antenna at Earth anymore. The signal was lost. The mission was over. It's worth pausing on that for a second. Ulysses didn't break. It didn't crash. It didn't fail because of a software bug or a mechanical fault. It died because the universe ran out its clock. The plutonium decayed. The heat faded. The cold won. And now the spacecraft is still up there, orbiting the Sun in silence, passing over the poles every 6 years, carrying instruments that no longer have power and an antenna that no longer points home. It's a ghost, a monument to a mission that worked far longer than anyone expected and still didn't get to finish everything it started. Ulysses was supposed to be the first of many polar missions. That was the hope. The data it sent back was so rich, so full of surprises, that scientists immediately started planning follow-up missions, larger spacecraft with better instruments, missions that could reach 90 degrees instead of 80, missions that could hover over the poles instead of just passing by. But those missions never got funded. The cost was too high. The science return, as valuable as it was, couldn't compete with missions to Mars, missions to the outer planets, missions that captured the public imagination in ways a solar polar orbiter never quite did. Ulysses remained alone, the only spacecraft to ever fly a polar orbit around the Sun. The first and, so far, the last. Which brings us back to the blind spot. Ulysses proved we could get out of the ecliptic. It proved the view from above was different and worth seeing. It measured things no one had measured before and found answers no one predicted, but it also revealed how much we still don't know. 80 degrees is not 90. Passing over the poles once every 6 years is not the same as staying there. The data Ulysses collected is extraordinary, but it's also limited. Snapshots taken from a moving platform at an angle. Enough to tell us the poles are different. Not enough to tell us everything about how they work. The Sun's poles are still mostly unexplored. The magnetic field there is still not fully understood. The processes that drive the solar wind at high latitudes are still being debated. And the question of what the Sun actually looks like from directly above, that perfect overhead view, the photograph we've never taken, remains unanswered. Ulysses got closer than anyone else, but it didn't close the gap. It just showed us how wide the gap really is. Ulysses showed us the poles. It gave us measurements. Data streams, magnetic field readings, particle counts. It proved the journey was possible and worth making. But here's what it didn't show us, what it couldn't show us from its tilted 80-degree orbit passing overhead every 6 years. It didn't show us the whole picture. It didn't reveal what the sun actually is when you stop thinking of it as a bright disk in the sky and start thinking of it as a three-dimensional object radiating outward in every direction at once, filling space with its presence in a way that extends far beyond the thin, flat plane we've spent our entire existence navigating through. The sun doesn't stop at its visible surface. That glowing sphere you see in photographs, the photosphere with its sunspots and granulation, is just the densest part of something much larger. The sun's atmosphere keeps going. The corona, that faint halo of superheated plasma visible during total solar eclipses, extends outward for millions of kilometers. And even that's not the edge. The corona doesn't have a hard boundary where it suddenly ends and space begins. Instead, it thins out gradually, and as it thins, it accelerates. The plasma escapes the sun's gravity and becomes the solar wind, a constant stream of charged particles, mostly electrons and protons, blowing outward in all directions at hundreds of kilometers per second. That wind doesn't stop at Earth. It doesn't stop at Jupiter. It keeps going, past Neptune, past the Kuiper Belt, out into the dark where the planets end and the space between stars begins, and the solar wind carries something with it, the sun's magnetic field. The field doesn't stay anchored to the sun's surface. It gets dragged along by the escaping plasma, stretched out into space like taffy being pulled. Because the sun rotates, the magnetic field doesn't point straight outward, it spirals. Imagine a lawn sprinkler spinning while it sprays water. The water doesn't shoot out in straight lines. It curves, following the rotation of the sprinkler head. The sun's magnetic field does the same thing, forming a structure called the Parker spiral, named after Eugene Parker, the physicist who predicted it in the 1950s. The field lines twist outward in a slow, graceful spiral, threading through the entire solar system and beyond. The solar wind and the magnetic field together create something called the heliosphere. That word breaks down simply. Helio, from the Greek word for sun, sphere, meaning a three-dimensional region surrounding a central point. The heliosphere is the sun's sphere of influence. It's the volume of space where the sun's magnetic field and solar wind dominate over the thin gas drifting between stars, and it is enormous, far larger than the solar system as most people picture it. NASA describes the heliosphere as a huge magnetic bubble. That's not a metaphor, it's a reasonably accurate description of the structure. The sun sits at the center, blowing a wind outward in all directions. That wind pushes against the interstellar medium, the extremely thin gas made mostly of hydrogen and helium that fills the space between stars. The interstellar medium pushes back. The result is a boundary, a region where the two pressures balance, and inside that boundary is the heliosphere. Everything inside the bubble, every planet, every asteroid, every comet, every spacecraft humanity has ever launched, all of it sits inside the sun's extended atmosphere. We are not floating in empty space, we are living inside a star's exhalation. The heliosphere is not symmetrical. If the sun were sitting still in a perfectly uniform interstellar medium, the bubble might be a neat sphere expanding evenly in all directions, but the sun isn't sitting still, it's moving. The entire solar system is orbiting the center of the Milky Way galaxy at about 220 kilometers per second, and as it moves, it plows through the interstellar medium like a boat moving through water. The front of the heliosphere, the side facing the direction the sun is moving, gets compressed by the oncoming interstellar gas. The backside, the wake, stretches out into a long tail, For years, the standard model described the heliosphere as comet-shaped, a rounded head in front, a long stretched tail behind, tens of billions of kilometers long. That model held for decades. Then in 2020, new data from NASA's Interstellar Boundary Explorer, a small spacecraft called IBEX that maps the edge of the heliosphere by detecting energetic neutral atoms bouncing back from the boundary, suggested the tail might not be as long as everyone thought. Some researchers started arguing the heliosphere looks less like a comet and more like a croissant. A rounded front, two lobes stretching backward, and a much shorter tail than the old models predicted. The jury is still out. The truth is, we don't have a spacecraft far enough outside the heliosphere to photograph it from a distance. All our data comes from instruments inside the bubble looking outward, trying to reconstruct the shape from indirect measurements. It's like being inside a house and trying to figure out what the house looks like from the street by bouncing tennis balls off the walls and listening to how long they take to come back. What we do know is the scale. The heliosphere extends outward to a distance of roughly 80 to 100 astronomical units from the Sun in most directions. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. Multiply that by 80 or 100 and you get a sense of how far the Sun's influence reaches. Pluto, at its farthest, orbits at about 49 astronomical units. The heliosphere's edge is roughly twice as far out as Pluto, and that edge has a name, the heliopause. The heliopause is not a wall, it's a transition zone, a boundary layer where the solar wind slows down, heats up, and eventually stops pushing outward because the pressure from the interstellar medium equals the pressure from the Sun. Cross the heliopause and you're in interstellar space. The solar wind is gone. The Sun's magnetic field no longer dominates. You're in the galaxy's medium, drifting through the thin gas between stars. It's still not empty. Space is never truly empty, but it's a different kind of not empty. The particles you're surrounded by didn't come from the Sun. They came from other stars, from supernovae, from the slow churn of the galaxy itself. Only 5 spacecraft have ever reached the heliopause. Voyager 1 crossed it in August 2012 at a distance of about 121 astronomical units from the Sun. Voyager 2 crossed in November 2018 at 119 astronomical units. Pioneer 10 and Pioneer 11, launched in the early 1970s, are also out there somewhere beyond the boundary, but both spacecraft stopped transmitting decades ago and we've lost contact. New Horizons, the probe that flew past Pluto in 2015, is still on its way out, currently about 60 astronomical units from the Sun and climbing. It won't reach the heliopause for another decade or more, but when it does, it'll become the 5th active spacecraft to leave the heliosphere and enter interstellar space. Here's the thing that matters. The heliosphere is not flat. It's not a disk. It's not confined to the ecliptic plane. It's a bubble, a 3-dimensional structure that extends above and below the plane of the planets, just as far as it extends outward along the plane. And the shape of that bubble, the way the solar wind flows through it, the way the magnetic field threads through it, all of that is controlled in large part by what's happening at the Sun's poles. The Sun rotates. At the equator, it completes 1 rotation every 25 days. At the poles, it takes closer to 34 days. That's called differential rotation, and it's one of the main reasons the Sun's magnetic field is so complicated. The equator spins faster than the poles, dragging the magnetic field lines with it, twisting them, tangling them, building up stress until the field snaps and reorganizes itself in a solar flare or a coronal mass ejection. But that's mostly an equatorial phenomenon. The poles don't have as much of that chaos. The magnetic field near the poles is simpler, more open, less tangled, and because the field is more open, the solar wind can escape more easily. That's why Ulysses measured faster solar wind speeds over the poles. The wind wasn't fighting its way through a maze of looping magnetic field lines. It was accelerating outward along open field lines that pointed straight out into space. Those open field lines at the poles shape the entire heliosphere. The solar wind doesn't blow uniformly in all directions. It's faster and smoother near the poles, slower and more variable near the equator. That difference in speed creates structure. The fast wind from the poles catches up with the slow wind from the equator, compressing it, forming regions called corrotating interaction regions where the two streams collide. Those collision zones can accelerate particles to high energies, creating bursts of radiation that ripple outward through the solar system. Spacecraft have detected these structures. Satellites near Earth have measured them. But most of the measurements, once again, come from instruments sitting in or near the ecliptic plane. The view from above, the view from below, remains mostly uncharted. The heliosphere matters for reasons that go beyond academic curiosity. It's not just a neat feature of the solar system that scientists like to study, it's a shield. The interstellar medium is full of cosmic rays, high-energy particles accelerated by supernova explosions, colliding neutron stars, black holes feeding on matter, all the violent processes happening out in the galaxy. Those particles are dangerous. They carry enough energy to damage DNA, disrupt electronics, degrade materials. If Earth sat directly in the interstellar medium with no protection, the surface radiation environment would be significantly worse than it is now. The heliosphere deflects most of those particles. The solar wind and the sun's magnetic field act like a buffer, pushing back against the cosmic rays, slowing them down, scattering them. Some still get through, especially during solar minimum when the sun's magnetic field is weaker, but the heliosphere blocks the majority. That shielding isn't uniform. It's stronger in some directions than others. The front of the heliosphere, the side facing the direction the sun is moving through the galaxy, is compressed and denser. The cosmic ray shielding there is better. The tail, stretched out behind, is thinner and less effective. Cosmic rays can penetrate more easily from the tail side. And the poles, with their open magnetic field lines, might offer less shielding than the equator, where the field is more tangled and complex. We don't know for sure. We've never had instruments in position to measure it properly. But the models suggest that if you wanted to travel through interstellar space and minimize your radiation exposure, you'd want to understand the three-dimensional structure of the heliosphere in detail so you'd know which direction offers the best natural protection. And here's where the missing perspective becomes a real problem. If humanity ever wants to send a probe to another star, and there are serious proposals to do exactly that, the spacecraft will have to leave the heliosphere. It'll have to cross the heliopause, enter interstellar space, and keep going for decades or centuries until it reaches its target. The path it takes out of the heliosphere matters. Launch along the ecliptic, and you're following the same route Voyager 1 and Voyager 2 took, threading through the equatorial regions where the solar wind is slower and more turbulent. Launch perpendicular to the ecliptic, straight up or straight down through the poles, and you're cutting through the fast solar wind, the open field lines, a potentially cleaner and faster route out of the bubble. But we don't have good data on what that route looks like. We don't know how thick the heliopause is at the poles. We don't know how the magnetic field behaves there. We don't know if there are structures, shocks, turbulence, regions of enhanced particle density that could damage a spacecraft's instruments or degrade its communications. Ulysses gave us a taste. It measured the polar solar wind. It tracked the magnetic field. It recorded cosmic rays streaming in from high latitudes. But Ulysses never left the heliosphere. Its orbit kept it inside, circling the sun every 6 years, never venturing out to the boundary. The heliopause, the place where the sun's influence ends and the galaxy begins, remains unexplored from any angle except the 2 narrow corridors Voyager 1 and Voyager 2 happened to cross through. Both of those crossings occurred in the ecliptic plane, one slightly above, one slightly below, but both essentially equatorial. The polar heliopause has never been visited. We have models, we have simulations, we have educated guesses, but we don't have data. There's another reason the heliosphere's 3-dimensional structure matters. The sun's magnetic field doesn't just point outward, it flips. Every 11 years, as the solar cycle progresses, the sun's north magnetic pole becomes the south magnetic pole, and the south becomes the north. The entire field reverses polarity. Scientists have known about this for decades, but they've never fully understood how the reversal propagates through the heliosphere. Does it happen simultaneously everywhere, or does the flip start at the poles and spread outward toward the equator over time? Does the heliopause change shape when the field reverses? Do the corrotating interaction regions shift? Does the cosmic ray shielding weaken or strengthen? Ulysses watched one complete field reversal from above. It recorded the collapse of the polar magnetic field during solar maximum, the period when the field was weakest and most disorganized, and then watched the field rebuild itself with the opposite polarity during the following solar minimum. The data showed that the reversal is a whole sun process, not just something happening at the surface. The field lines that extend out into the heliosphere reverse too, carried outward by the solar wind over a span of months or years. But Ulysses was only one spacecraft at one set of locations. It couldn't map the entire heliosphere simultaneously. It couldn't tell us how the field reversal looked from the heliopause, or from the tail, or from the compressed nose where the sun is plowing into the interstellar medium. Those gaps remain. The heliosphere is also not static. It breathes, it expands and contracts depending on the solar cycle. During solar maximum, when the sun is active and covered in sunspots, the solar wind is stronger and the heliosphere pushes outward, growing slightly larger. During solar minimum, when the sun quiets down, the wind weakens and the heliosphere shrinks. The change isn't dramatic, maybe 10 or 20% in radius, but it's enough to move the heliopause inward or outward by tens of astronomical units. Voyager 1 and Voyager 2 both detected fluctuations in the boundary as they crossed it, regions where the solar wind seemed to stop and start again, as if the heliopause were rippling or oscillating. Some researchers think those ripples are caused by changes in the solar wind pressure as the sun cycles through its activity phases. Others think they're caused by variations in the interstellar medium, density waves, or turbulence in the galactic gas that the heliosphere is moving through. Without more data points, without spacecraft crossing the heliopause at different latitudes and different times, it's hard to tell which explanation is right. And then there's the tail, the heliotail, the wake stretching out behind the sun as it moves through the galaxy. Is it long and narrow like a comet's tail? Or is it short and bifurcated like the croissant model suggests? Does it twist or kink as the sun's magnetic field rotates? Does it shed blobs of plasma the way a comet sheds material as it heats up near the sun? We don't know. No spacecraft has ever flown down the heliotail. No instrument has ever mapped it. The data we have comes from indirect measurements, energetic neutral atoms detected by IBEX bouncing back from the tail region, and theoretical models that try to match those observations to the physics of how plasmas behave under pressure. The models disagree. Some say the tail is 100 astronomical units long, some say it's 200. Some say it's barely there at all, just a diffuse cloud of solar wind that mixes into the interstellar medium within a few dozen astronomical units of the heliopause. All of those models are consistent with the available data, which tells you how sparse the data really is. Here's the frustrating part. The heliosphere is not some distant abstract structure. It's right here. We are inside it. Every breath you take, every photon of sunlight hitting your skin, every charged particle deflected by Earth's magnetic field before it can reach the atmosphere, all of it is happening inside the heliosphere. This is the environment we live in. This is the immediate cosmic neighborhood. And we've barely scratched the surface of understanding its full three-dimensional shape because we've spent 70 years exploring it from a single narrow angle. The sun's influence is not a flat disk, it's a sphere, a bubble, a living, breathing structure that pulses with the solar cycle, that spirals with the sun's rotation, that pushes outward against the galaxy and carves out a pocket of space where the conditions are just calm enough for planets to form and life to take hold. Understanding that structure means stepping outside the Flatland. It means climbing out of the Ecliptic and looking back from above or below, seeing the whole picture instead of just the cross-section. Ulysses proved it could be done. It reached the poles. It measured the solar wind, the magnetic field, the cosmic rays. It gave us the first real glimpse of what the sun looks like from outside the plane. And then it went silent, and no one followed. The missions that could have picked up where Ulysses left off never got funded. The instruments that could have mapped the heliosphere in 3 dimensions never got built. The spacecraft that could have flown through the polar heliopause and sent back data from the other side never launched. The gap Ulysses opened is still there, wider now than it was 20 years ago, and no one is moving to close it. We live inside a bubble, the sun's bubble, a structure so vast it takes light more than a day to cross from one side to the other, so dynamic it reshapes itself every 11 years, so essential to our survival that without it the surface of Earth would be scoured by radiation from the galaxy. And we've mapped maybe 10% of it. The rest remains invisible, inferred, guessed at. We know it's there because the physics says it has to be, but we haven't seen it, we haven't measured it, we haven't pointed a camera at it from the one angle that would show us the whole thing at once. That angle exists, 90 degrees above the sun. Looking straight down at the pole, watching the solar wind stream outward in every direction, seeing the magnetic field spiral outward from the rotational axis, tracing the shape of the heliosphere as it stretches away into the dark. The photograph is possible. The mission is possible. The trajectory is hard, but not impossible. Someone just has to decide it's worth the cost. Until then, we're still living in Flatland. Still drawing maps from inside the plane. Still inferring the shape of the bubble from measurements taken at the equator, and trying to convince ourselves we understand the whole picture. The sun has poles, the heliosphere has structure, and somewhere above us, 90 degrees out of reach, there's a view we've never seen and a story we've never finished telling. We've been talking about the sun as if it sits in empty space, as if the heliosphere, that enormous bubble of solar wind and magnetic field stretching out 100 astronomical units in every direction, is pushing against nothing, a void, the vacuum. But that's not true. Space isn't empty. It never has been, and the sun isn't floating alone in the dark. It's traveling, moving through something, and that something has a name: the local bubble. Before we get to what the local bubble is, you need to understand where the sun sits in the galaxy. The Milky Way is a spiral galaxy, a flat rotating disk of stars, gas and dust, about 100,000 light-years across, and, depending on how you measure it, somewhere between 1,000 and 3,000 light-years thick through most of the disk. The Sun orbits the galactic center at a distance of roughly 26,000 light-years, moving at about 220 kilometers per second. One full orbit takes approximately 230 million years. The last time the Sun was in this exact spot in the galaxy, dinosaurs were just starting to diversify on Earth. The time before that, complex life hadn't yet crawled onto land. The Sun doesn't sit in the main plane of the Milky Way's disk. It sits slightly above it, in a structure called the Orion Spur, sometimes called the Orion Arm. The Orion Spur is a minor spiral arm, a sort of connecting bridge between two of the galaxy's major arms, the Perseus Arm and the Sagittarius Arm. It's a dense region by galactic standards, full of young hot stars, star-forming regions, and clouds of gas and dust. The Sun is one of the older, quieter stars in the neighborhood. Most of its neighbors are younger, brighter, and more violent. And the Sun is moving through all of this, not just orbiting the galactic center in a neat circle, but bobbing up and down through the plane of the galaxy as it goes. The motion is like a slow sine wave. The Sun crosses through the galactic midplane, drifts upward for tens of millions of years, slows, stops, and falls back down, crossing the midplane again and continuing downward before rising again. The full cycle takes somewhere between 60 and 70 million years. Right now, the Sun is above the midplane, about 50 light-years above it, and drifting higher. In another 10 or 15 million years, it'll reach the peak of its current oscillation, roughly 250 light-years above the plane, then start falling back. This bobbing motion matters because the Milky Way isn't uniform. The midplane is where most of the galaxy's gas and dust concentrate. It's also where most of the star formation happens, which means it's where most of the supernovae happen. Supernovae are the explosive deaths of massive stars, and they don't just destroy the star. They blast enormous amounts of energy and material into the surrounding space, carving out cavities in the interstellar medium, heating the gas to millions of degrees, and sending shockwaves rippling outward for hundreds of light-years. When the Sun is near the midplane, it's more likely to be close to active star-forming regions and more likely to be affected by nearby supernovae. When it's farther from the midplane, like it is now, the environment is calmer, fewer massive stars, fewer explosions, less chaos. But calm is relative. The space the Sun is moving through right now is anything but quiet. It's sitting inside a bubble, a cavity, a region of space where the interstellar medium, the thin gas that fills the space between stars, has been blown away, leaving behind a hot, low-density void roughly 1,000 light-years across. That void is the local bubble, and the Sun is deep inside it. The interstellar medium is mostly hydrogen, with some helium and trace amounts of heavier elements. In a typical region of the galaxy, the density of the interstellar medium is about 1 atom per cubic centimeter. That sounds empty. It is empty by any human standard, but in a galaxy, that 1 atom per cubic centimeter adds up. Over distances of light-years, it's enough to absorb starlight, scatter radiation, and shape the environment stars live in. Inside the local bubble, the density drops to about 1/10 of that, 0.1 atoms per cubic centimeter, 10 times emptier than the space around it. The gas that should be here was blown away. How? Supernovae, lots of them. The current model, the one most astronomers agree on, says the local bubble was carved out by somewhere between 10 and 20 supernova explosions over the last 10 to 15 million years. Those explosions didn't happen randomly. They happened in a cluster, a group of massive stars that formed together, lived fast, and died young, one after another. Each supernova added to the cavity, pushing the gas outward, heating it, expanding the bubble. The shock waves from those explosions are still echoing through the region, keeping the interior of the bubble hot, around 1,000,000 degrees Kelvin, and preventing the interstellar gas from collapsing back inward. 1,000,000 degrees sounds catastrophic. It's not. The gas is so thin that even at 1,000,000 degrees, the total amount of energy in any given cubic meter is negligible. If you could somehow stand in the middle of the local bubble without a spacesuit, you wouldn't burn. You'd freeze because there aren't enough particles hitting you to transfer heat. Temperature and heat are not the same thing. Temperature measures the average energy of individual particles. Heat measures the total energy transfer. In the local bubble, the particles are extremely energetic, but there are so few of them that the net effect is almost nothing. A spacecraft flying through the bubble wouldn't even notice it was there unless it had instruments sensitive enough to detect the faint glow of hot ionized gas filling the void. The Sun entered the local bubble somewhere between 5 and 10 million years ago, depending on which reconstruction of the Sun's galactic orbit you trust. Before that, it was outside, moving through denser regions of the interstellar medium where the gas pressure was higher and the cosmic ray flux was different. The transition from outside the bubble to inside would have been gradual, taking hundreds of thousands of years as the Sun drifted across the boundary. The heliosphere would have expanded slightly as the external pressure from the interstellar medium dropped. The cosmic ray environment around Earth would have shifted. Some researchers think that shift might have had measurable effects on Earth's climate, though the evidence is disputed. Cosmic rays can seed cloud formation in the atmosphere by ionizing air molecules, and more cosmic rays mean more clouds, which means more sunlight reflected back into space, which means cooling. If the Sun's entry into the local bubble changed the cosmic ray flux reaching Earth, it could have nudged the climate in one direction or another. Maybe. The signal is small and hard to separate from all the other things that affect climate over millions of years. What's not disputed is that the local bubble has shaped the solar neighborhood. The Sun isn't the only star inside the bubble. There are hundreds of other stars drifting through it, most of them smaller and dimmer than the Sun. Some of them are young, formed in the last few million years from gas that collapsed along the edges of the bubble where the density is higher. Others, like the Sun, are older and just passing through. The bubble is not a permanent structure. It will fade eventually. In another few million years, the hot gas inside will cool, the pressure will drop, and the interstellar medium will start flowing back in, refilling the cavity. The local bubble will collapse, and the Sun will drift out the other side, moving into whatever region of the galaxy comes next. But for now, this is home. The Sun, the solar system, the heliosphere, all of it sits inside this enormous cavity carved out by the deaths of stars that no longer exist. We're living in the aftermath of explosions that happened millions of years before humans existed. The light from those supernovae has long since faded. The stars that exploded are gone. Their cores collapsed into neutron stars or black holes, their outer layers dispersed into the interstellar medium. But the bubble they left behind is still here, and we're inside it. The local bubble is part of a larger structure. The Milky Way's disk is full of bubbles like this, cavities carved out by supernovae and stellar winds from massive stars. Some are smaller than the local bubble, some are larger. They overlap, merge, form chains and networks that thread through the galaxy. Astronomers call this the interstellar medium's foam structure. The dense gas collects in sheets and filaments between the bubbles. The bubbles themselves are filled with hot, thin gas that glows faintly in X-rays. From a distance, if you could see the Milky Way's interstellar medium in X-rays, it would look like Swiss cheese, holes everywhere, surrounded by denser material with stars scattered throughout. The Sun's position inside the local bubble affects more than just the density of the gas it's moving through. It affects the radiation environment. Cosmic rays, high-energy particles from outside the solar system, are partially blocked by the interstellar medium. In denser regions of the galaxy, where the gas is thicker, cosmic rays scatter and lose energy as they pass through. Inside the local bubble, the gas is thinner, which means cosmic rays can penetrate more easily. The heliosphere still blocks most of them, but the ones that do get through have an easier path. That has implications for long-term radiation exposure on planets, for the evolution of atmospheres, for the survival of life in general. Earth's magnetic field and atmosphere provide additional shielding, so the effect here is minimal. But for a planet without a strong magnetic field, sitting inside a bubble like this could mean a significantly harsher radiation environment. There's another layer to this. The local bubble isn't the smallest structure the Sun sits inside. Nested within the bubble is something smaller, called the local interstellar cloud. That's the cloud of gas the solar system is currently moving through, the immediate neighborhood, only about 30 light-years across. The local interstellar cloud is part of the bubble's wall, a denser patch of material that hasn't been completely swept away by the supernovae that created the cavity. The Sun entered the local interstellar cloud within the last 100,000 years and will exit it in another 10 to 20,000 years. That cloud is what the heliosphere is directly pushing against. It's the source of the interstellar neutral atoms that IBEX detects streaming into the solar system. It's the medium the heliopause is shaped by. So here's the stack. The Milky Way galaxy. Inside that, the Orion spur. Inside that, the local bubble, a cavity 1,000 light-years wide carved out by supernovae. Inside that, the local interstellar cloud, a 30 light-year wide patch of denser gas. Inside that, the heliosphere, the Sun's magnetic bubble extending about 100 astronomical units from the Sun. Inside that, the solar system, the planets, the ecliptic plane. Inside that, Earth. And on Earth, us, trying to make sense of all these nested layers of structure, trying to map the environment we're embedded in, trying to understand how everything from the galaxy down to the ground beneath our feet connects. The problem is perspective. The Milky Way is a disk, a flat disk. When we look at images of the galaxy, they're almost always edge-on or face-on views, drawn from some imaginary vantage point outside the galaxy looking back. But we're not outside. We're inside, embedded in the disk, 26,000 light-years from the center, 50 light-years above the midplane. The view from here is not clean. When we look toward the galactic center, we're looking through the disk edge-on, through thousands of light-years of gas and dust that block most of the light. When we look perpendicular to the disk, straight up toward the galactic North Pole or straight down toward the South Pole, we're looking out of the disk through much less material, which is why those directions are clearer. Astronomers have mapped the galaxy by piecing together observations from our one fixed viewpoint, inferring structure from the motion of stars, the distribution of gas, the positions of distant objects. It works, but it's incomplete. Now take that same problem and shrink it down to the solar system. We're embedded in the ecliptic plane. We've spent 70 years mapping the Sun, the planets, the heliosphere, all from within that plane. We've inferred the three-dimensional structure of the Sun's magnetic field, the shape of the heliosphere, the behavior of the solar wind at high latitudes, all from measurements taken at low latitudes and models that try to extrapolate upward. It works, but it's incomplete. The same way our view of the Milky Way is incomplete because we're stuck inside the disk. Our view of the solar system is incomplete because we're stuck inside the ecliptic plane. Ulysses broke out of the plane and gave us the first real data from high solar latitudes. It showed us the sun's poles, the fast solar wind, the open magnetic field lines, the cosmic ray flux streaming in from outside the heliosphere. It proved the view from above was worth seeing. But Ulysses stayed inside the heliosphere. It never crossed the heliopause. It never reached the edge of the local interstellar cloud. It never climbed high enough to see the sun's bubble from outside, to map how the heliosphere fits into the larger structure of the interstellar medium. We have one data point for what the heliopause looks like. Voyager 1 crossed it in the ecliptic plane at about 121 astronomical units from the Sun. Voyager 2 crossed it at 119 astronomical units, slightly south of the ecliptic. Both spacecraft detected a sharp transition, a boundary where the solar wind stopped and the interstellar medium began, but they crossed at nearly the same latitude. They sampled 2 points on the equator of the heliosphere. The poles remain unexplored. Does the heliopause sit closer to the Sun at the poles because the solar wind is faster there and pushes harder against the interstellar medium? Or does it sit farther out because the open magnetic field lines allow the solar wind to escape more easily? We don't know. The models disagree. Some say the heliosphere is more spherical than we think. Some say it's flattened, compressed along the poles, and stretched along the equator. Some say the shape depends on the phase of the solar cycle, that it breathes in and out over 11 years, changing its aspect ratio as the solar wind waxes and wanes. All of those models are consistent with the 2 data points we have, which tells you how little we actually know. The local bubble complicates the picture. The heliopause is shaped by the balance between the solar wind pushing outward and the interstellar medium pushing inward. Inside the local bubble, the interstellar medium is thinner and hotter than it is in most regions of the galaxy. That means the external pressure on the heliosphere is lower. If the Sun were sitting in a denser region, the heliopause would be closer, squeezed inward by the higher pressure of the surrounding gas. Inside the bubble, the heliosphere can expand farther. Some estimates suggest the heliosphere is 20 to 30% larger than it would be if the Sun were outside the bubble. That extra breathing room might matter. It might give Earth and the other planets a little more shielding from cosmic rays. It might change the radiation environment at the edge of the solar system. It might affect how quickly spacecraft like Voyager or New Horizons can reach interstellar space. But again, we don't know. We have 2 crossings of the heliopause, both at the equator, both in the same phase of the solar cycle, both in the same local environment. We need more data points. We need crossings at different latitudes, different times, different directions. We need to map the heliopause the way we've started to map the rest of the heliosphere in 3 dimensions over time, with enough resolution to see how it changes and what drives those changes. The local bubble also matters for thinking about life. Earth is habitable, that's obvious. But habitability isn't just about being in the right temperature zone around the right kind of star. It's about the environment that star sits in. A star in a dense star-forming region, surrounded by massive young stars that explode as supernovae every few million years, is a more dangerous place for life than a star in a quiet region like the local bubble. Supernovae don't just release light and heat. They release gamma rays, X-rays, high-energy particles that can strip away planetary atmospheres, sterilize surfaces, and disrupt the chemistry that life depends on. If a supernova goes off within a few tens of light-years of a planet, the radiation could be catastrophic. The Sun's current position, 50 light-years above the galactic midplane, inside a bubble that's already been cleared of massive stars, is relatively safe. There are no nearby supernova candidates. The closest massive star that might explode in the near future is Betelgeuse, about 550 light-years away. That's far enough that even if it went supernova tomorrow, the radiation reaching Earth would be noticeable but not dangerous. We'd see a bright new star in the sky for a few months. It would be brighter than the full moon, and then it would fade. Life would go on. But the sun hasn't always been this safe. 15 million years ago, when the local bubble was being carved out, the sun might have been much closer to the supernovae that created it. Some reconstructions of the sun's orbit suggest it was near the edge of the region where the explosions were happening, close enough that Earth could have been exposed to elevated levels of radiation. There's some evidence, disputed but intriguing, that Earth's fossil record shows an increase in cosmic ray exposure around that time. Isotopes like iron-60, which are produced in supernovae and don't occur naturally on Earth, have been found in deep-sea sediments dating to roughly 2 to 3 million years ago. That suggests a nearby supernova deposited material in Earth's atmosphere that eventually settled on the ocean floor. The amounts are small, the effects on life were probably minimal, but it's a reminder that the galaxy is not a static backdrop. The sun moves, the neighborhood changes, and every few tens of millions of years, Earth drifts through regions where the radiation environment is different. The local bubble won't last forever. In a few million years, the hot gas inside will cool, the pressure will drop, and the bubble will start to collapse. The interstellar medium will flow back in, refilling the cavity, and the sun will move on to the next region, whatever that turns out to be. Maybe denser, maybe quieter, maybe another bubble. The galaxy is full of them. The sun's orbit carries it through a constantly shifting landscape of gas, dust, stars, and voids. Every environment the sun passes through leaves a faint signature in the solar system, in the planet's atmospheres, in the cosmic ray flux, in the structure of the heliosphere. If you could read those signatures, you could reconstruct the sun's entire journey through the galaxy over billions of years. Some scientists are trying to do exactly that, using isotopes in meteorites, in lunar samples, in ice cores, to trace the sun's history. It's like reading tree rings, except the tree is the solar system and the rings are written in radioactive atoms deposited by long-dead stars. This is the context Ulysses was missing. It mapped the sun's poles. It measured the solar wind, the magnetic field, the cosmic rays streaming in from high latitudes, but it never climbed high enough to see how the heliosphere fits into the local bubble. It never crossed the boundary and looked back. It never gave us the photograph of the sun sitting in its cavity, the heliosphere glowing faintly against the backdrop of the surrounding interstellar medium. That photograph would show us scale. It would show us how small the solar system is compared to the bubble it sits inside. It would show us how the sun's influence, as vast as it seems from inside, is just a tiny pocket of order carved out of the galaxy's chaos. And it would show us something else. The flatland we've been living in, the ecliptic plane, isn't just a limit we've imposed on ourselves by building missions that stay in the plane. It's a consequence of where we are. Earth sits in the ecliptic. Our telescopes sit on Earth. Our perspective is locked to the plane by the simple fact that we're embedded in it. To see the sun from above, we'd have to leave not just the ecliptic, but the solar system itself, climb up out of the heliosphere, out of the local interstellar cloud, far enough that the sun becomes just another star in the sky, a bright point surrounded by a faint bubble, one object among billions drifting through the galaxy. No one has done that. No spacecraft has gone that far. Voyager 1 and Voyager 2 are outside the heliosphere now, but they're still close, still within a few light days of the sun, still moving outward along trajectories that stay roughly in the ecliptic plane. They're not climbing, they're coasting. And they'll keep coasting for tens of thousands of years before they drift far enough to lose sight of the sun entirely. By then, their power will have run out. Their transmitters will have gone silent. They'll be derelict, ancient machines carrying messages from a civilization that might not exist anymore, drifting through a galaxy that doesn't care, but they'll still be there, and the local bubble will still be there, and the sun will still be drifting through it, pulling its retinue of planets along, moving toward whatever comes next. Somewhere ahead, past the edge of the bubble, the interstellar medium thickens again. The sun will cross that boundary in another few million years, and the heliosphere will shrink, compressed by the higher external pressure. The cosmic ray environment will shift. Earth's climate might shift with it, and life, if it's still here, will adapt, the way it always has, to whatever new conditions the galaxy imposes. We are not separate from the galaxy. We live inside it. The sun's radiation, the Heliosphere's shielding, the local bubble's emptiness, the Milky Way's spiral arms, all of it shapes the environment Earth exists in, and we've spent our entire history looking at that environment from one narrow angle, from inside the Flatland, inferring the rest from models and mathematics. Ulysses gave us a glimpse of what we were missing. It proved the poles were different. It proved the view from above mattered. But it didn't finish the job. The heliopause is still unexplored at high latitudes. The sun's bubble is still unmapped in 3 dimensions. The photograph is still missing. The tools exist. The trajectories are possible. A spacecraft could reach the polar heliopause. It would take decades. It would cost billions. But it's not physically impossible. It's just expensive. And in an era where space exploration budgets are tight and every mission has to justify itself against a dozen competing priorities, expensive means unlikely. The missions that get funded are the ones that promise discoveries the public can understand: life on Mars, oceans on Europa, rings around Saturn. A mission to map the heliosphere's polar structure doesn't have that kind of appeal. It's abstract, it's technical, it's the kind of science that matters deeply to a small community of researchers and doesn't make headlines, but it should, because the heliosphere is not an abstract structure. It's the boundary of our home. It's the shell that separates the solar system from the galaxy. It's the first line of defense against the radiation and chaos of interstellar space, and we've barely begun to understand it. We've mapped the equator, we've glimpsed the poles, but the whole picture, the 3-dimensional structure, the way it breathes and shifts and responds to the galaxy around it, remains out of reach until someone builds the mission that can climb high enough to see it, until someone points a camera 90 degrees above the sun and captures the view we've never had, until someone finishes what Ulysses started. The photograph is out there, the angle exists, the technology exists. All that's missing is the will to go and take it. We've been circling the problem for a while now. The ecliptic is a trap. The sun's poles remain unexplored. The heliosphere is unmapped in 3 dimensions. Ulysses proved we could get there, but no one followed. And every time someone proposes a new mission to fly above or below the plane, the answer comes back the same: too expensive, too much fuel, not enough budget. The physics says we can't just point a rocket upward and burn our way out. We'd need more velocity than any chemical rocket ever built could provide. So the question becomes, if burning fuel won't work, what will? And the answer, the only real answer we've found in 70 years of spaceflight, is to cheat, to steal velocity from something bigger, to use gravity. The maneuver has a formal name: gravitational assist. But most people call it a gravity slingshot, and that's a better description of what actually happens. You fly a spacecraft past a planet, close enough that the planet's gravity grabs it, bends its trajectory, and flings it off in a new direction at a new speed. The spacecraft doesn't burn fuel. It doesn't fire its engines. It just falls past the planet and gets thrown out the other side like a stone whipped around on the end of a rope. It's one of the most elegant tricks in orbital mechanics, and it's the reason humanity has been able to explore the outer solar system at all. Without gravity assists, Voyager wouldn't have reached Neptune. Cassini wouldn't have reached Saturn. New Horizons wouldn't have reached Pluto. And Ulysses wouldn't have climbed out of the Ecliptic to see the sun's poles. Here's how it works. Imagine you're standing on the side of a highway and a truck drives past you at 100 kilometers per hour. You throw a baseball at the side of the truck as it passes. If you throw it in the same direction the truck is moving, the ball hits the truck, bounces off and comes back toward you faster than you threw it because it picked up some of the truck's speed. If you throw it in the opposite direction, against the truck's motion, the ball bounces back slower. The ball didn't gain or lose energy in the truck's frame of reference. In the truck's frame, the ball just bounced elastically off a hard surface. But in your frame, standing on the side of the road, the ball either sped up or slowed down depending on which way the truck was moving relative to the throw. That's essentially what a gravity assist does. The spacecraft is the baseball, the planet is the truck, and the reference frame that matters is the sun's. A spacecraft approaching a planet from behind, flying in the same direction the planet is orbiting, can steal a little bit of the planet's orbital momentum. The planet pulls the spacecraft forward, accelerating it, and then lets it go. From the planet's perspective, the spacecraft came in at a certain speed and left at the same speed, just in a different direction. But from the sun's perspective, the spacecraft gained velocity. It's moving faster than it was before the flyby. The planet, in turn, lost a tiny, infinitesimal amount of speed, but because the planet is billions of times more massive than the spacecraft, the effect on the planet is unmeasurable. The spacecraft, on the other hand, can gain kilometers per second of velocity for free, no fuel burned, no engines fired. Just gravity doing the work. If you approach the planet from the front, flying against its orbital motion, the opposite happens. The planet's gravity slows you down, you lose velocity. The spacecraft comes out the other side, moving slower in the sun's frame. That's less useful for missions trying to reach the outer solar system, but it's extremely useful if you want to fall inward toward the sun. Several solar missions have used Venus flybys to shed velocity and drop into tighter, faster orbits around the sun. Parker Solar Probe does this repeatedly. It swings past Venus, loses speed, and falls closer to the sun on each pass. The amount of velocity you gain or lose depends on a few things: the planet's mass, the planet's orbital speed, and how close you get. The closer the flyby, the stronger the gravitational pull, and the more dramatic the trajectory change. A spacecraft skimming just above a planet's atmosphere will experience a much larger velocity change than one passing at a safe distance of several planetary radii. That's why mission planners aim for low-altitude flybys whenever possible. The risk is higher, there's less room for navigation errors, but the payoff is enormous. Jupiter is the king of gravity assists. It's the most massive planet in the solar system by a wide margin, weighing in at about 318 times the mass of Earth, and it's moving fast, orbiting the Sun at roughly 13 kilometers per second. A spacecraft flying past Jupiter at the right angle can pick up enough velocity to escape the solar system entirely. That's what happened to Pioneer 10, the first spacecraft to use a gravity assist to reach escape velocity. It flew past Jupiter in December 1973, got flung outward, and never looked back. It's still out there somewhere, drifting through interstellar space, though we lost contact with it decades ago. Voyager 1 and Voyager 2 used Jupiter the same way. Both spacecraft launched in 1977 during a rare alignment of the outer planets that only happens once every 175 years. The alignment meant a spacecraft could fly from Jupiter to Saturn to Uranus to Neptune, using gravity assists at each stop to pick up speed and change direction without carrying enough fuel to do it alone. Voyager 1 launched in September and took a faster trajectory, reaching Jupiter in March 1979, then swinging past Saturn in November 1980. The Saturn flyby was aimed specifically at Titan, Saturn's largest moon, which meant the trajectory bent Voyager 1 upward out of the ecliptic plane at a steep angle. That wasn't the original goal. The goal was to study Titan. But the side effect was that Voyager 1 ended up climbing out of the plane at about 35 degrees, eventually crossing the heliopause in 2012 at a point well above the ecliptic. Voyager 2 launched in August 1977, a few weeks before Voyager 1, but took a slower route. It reached Jupiter in July 1979, then Saturn in August 1981, Uranus in January 1986, and Neptune in August 1989. Each flyby used gravity to accelerate the spacecraft and bend its path toward the next target. The Neptune encounter sent Voyager 2 downward, diving below the ecliptic at an angle of about 48 degrees. It crossed the heliopause in November 2018, becoming the second spacecraft to enter interstellar space. Both Voyagers are still transmitting faint signals back to Earth, though their power is fading and they'll go silent within the next decade. The Voyager missions proved that gravity assists could take you almost anywhere in the solar system if you were willing to wait and if the planets lined up correctly. But they also highlighted the limitations. A gravity assist can change your speed and direction, but it can't change them arbitrarily. The geometry matters. The planet has to be in the right place at the right time. The spacecraft has to approach from the right angle, and the resulting trajectory is determined by the laws of physics, not by what the mission planners wish would happen. You can't just pick a direction and slingshot yourself there. You have to work within the constraints the planets give you. Cassini used gravity assists more than any other mission. It launched in October 1997 on a trajectory that took it first to Venus, not away from the Sun but inward. It flew past Venus once in April 1998, then looped back around the Sun and flew past Venus again in June 1999. Each Venus flyby added velocity, accelerating Cassini as it fell deeper into the Sun's gravity well. Then it swung past Earth in August 1999, picking up more speed, and finally headed outward to Jupiter. The Jupiter flyby in December 2000 gave Cassini the final kick it needed to reach Saturn. 4 gravity assists, 3 different planets, 7 years of flying, all to deliver a spacecraft to Saturn that could never have gotten there on its own fuel. Once Cassini arrived at Saturn in July 2004, it used gravity assists from Titan, Saturn's largest moon, to reshape its orbit over and over again. Titan is massive enough and close enough that Cassini could fly past it every few weeks, using each flyby to tilt its orbit, raise or lower its altitude, change its inclination. Over the course of 13 years, Cassini performed more than 100 Titan flybys, each one tweaking the orbit slightly, allowing the spacecraft to explore Saturn's system from dozens of different angles. By the end of the mission, Cassini's orbit was tilted well out of Saturn's equatorial plane, taking it high above and below the rings. That was only possible because Titan was there to provide repeated gravity assists. Without Titan, Cassini would have been stuck in the same orbital plane for the entire mission. The lesson from Cassini is that gravity assists aren't just for getting to a destination, they're for reshaping orbits once you arrive. And that's the key to understanding how a future mission could reach the Sun's poles. You don't aim directly for a polar orbit. You can't. The velocity change required is too large. Instead, you aim for Jupiter, use Jupiter's gravity to tilt your orbit, and then coast up and over the Sun on the trajectory Jupiter gives you. That's what Ulysses did, and it worked. The question is whether it's possible to do better, to reach a full 90-degree inclination instead of 80, to climb higher, stay longer, map more. The answer is yes, but it's not simple. Reaching 90 degrees requires a more extreme flyby than Ulysses managed. Ulysses passed Jupiter at a distance of about 409,000 kilometers above the cloud tops. That's very close, well inside the orbit of Io, Jupiter's innermost large moon. The flyby bent Ulysses's trajectory by roughly 80 degrees out of the ecliptic plane. To reach 90 degrees, you'd need to get even closer, or approach from a slightly different angle, or both. The closer you get, the stronger the gravitational pull, and the more you can bend the trajectory. But there are limits. Fly too close and you start hitting other problems. Radiation. Jupiter's magnetosphere is filled with high-energy particles trapped by the planet's magnetic field. The radiation environment near Jupiter is intense enough to damage spacecraft electronics unless they're heavily shielded. Ulysses was built to survive the flyby, but it wasn't designed to linger. It flew through the radiation belts as quickly as possible and got out. Getting closer would mean more radiation exposure. It would also mean tighter navigation tolerances. A flyby altitude error of a few hundred kilometers might not matter much if you're passing at a safe distance, but at very low altitudes, a few hundred kilometers could be the difference between a successful gravity assist and a trajectory that sends you somewhere completely different, or worse, into Jupiter itself. Mission planners are cautious. They build in margins. They don't push the limits unless they absolutely have to. So a 90-degree inclination is possible in theory, but it's not something you'd design lightly. You'd need a spacecraft tough enough to handle the radiation, precise enough to hit the navigation target, and well-funded enough to afford the extra engineering. There's another option. Use multiple gravity assists. Instead of trying to get all the way to 90 degrees with a single Jupiter flyby, you could do it in stages. Fly past Jupiter once to tilt your orbit partway out of the ecliptic. Then fly past Saturn, using Saturn's gravity to tilt it further. Then come back for another Jupiter pass if the orbits line up correctly. Each assist adds a little more inclination, and eventually you reach 90 degrees. The problem is time. Each gravity assist adds years to the mission timeline. Ulysses took 16 months just to get to Jupiter for its first flyby. A mission using multiple assists could take a decade or more just to reach the desired orbit, and that's before you start collecting science data. Funding a mission that takes that long is hard. The scientists who propose it might retire before it launches. The engineers who build it might retire before it arrives. And the public, if they're paying attention at all, will have moved on to other things. But it's doable. Cassini proved that multi-assist trajectories can work. The Voyagers proved that you can visit multiple planets in sequence if the alignment is right. The tools exist. The physics is well understood. What's missing is the will to fund it and the patience to wait for the results. There's a subtler point here that's worth understanding. When a spacecraft gets a gravity assist, the planet doesn't just change the spacecraft's speed, it changes the direction. And direction matters just as much as speed when you're trying to get out of the ecliptic. The ecliptic is defined by the plane in which the planets orbit. If you want to leave that plane, you need to change your velocity vector so it points up or down, perpendicular to the plane. A gravity assist can rotate that vector. Approach a planet from one side, and the planet's gravity bends your path in one direction. Approach from the other side, and it bends your path the opposite way. The trick is to approach from the angle that bends your velocity vector as close to vertical as possible. Jupiter's orbit is almost perfectly aligned with the ecliptic. It's tilted by only about 1.3 degrees. That makes Jupiter a nearly ideal target for inclination changes because its gravity can pull you cleanly out of the plane without also pulling you sideways into some weird elongated orbit. Saturn is tilted by about 2.5 degrees, still close enough to work. Uranus is tilted by less than 1 degree, Neptune by less than 2. All of the giant planets are good candidates for gravity assists out of the ecliptic, but Jupiter is the best because it's the closest, the most massive and the fastest orbiting. You get the most bang for your buck with Jupiter. There's one more complication. The planets move. Their positions in their orbits change over time. A trajectory that works perfectly when Jupiter is on one side of the Sun might not work at all when Jupiter is on the other side. Launch windows for gravity assist missions are narrow. Sometimes they're measured in weeks or even days. Miss the window, and you have to wait for the planets to come back into alignment, which could take years. The Voyager Grand Tour alignment happens once every 175 years. If NASA had waited, if the missions had been delayed or cancelled, the opportunity would have been lost for lifetimes. The next Grand Tour window won't open until the 2050s. Anyone alive today who's older than about 60 probably won't live to see it. For a mission to the Sun's poles, the launch window depends on where Jupiter is and where you want to go. If you're aiming for the Sun's north pole, you need to approach Jupiter from the south and let the flyby throw you upward. If you're aiming for the south pole, you approach from the north. The timing has to be right. The spacecraft has to arrive at Jupiter when Jupiter is in the correct position relative to the Sun and relative to the spacecraft's incoming trajectory. That kind of precision requires years of mission planning, trajectory optimization, and sometimes a little bit of luck. Engineers can calculate the ideal trajectories, but they can't move the planets. If the alignment isn't there, the mission doesn't happen. Despite all these constraints, gravity assists remain the only practical way to reach high inclinations. Direct burns, where a spacecraft uses its own engines to tilt its orbit, are prohibitively expensive in terms of fuel. The amount of velocity change required to go from a 0-degree inclination to a 90-degree inclination while staying at roughly the same distance from the Sun is about 42 kilometers per second. That's more than 4 times the velocity a spacecraft gains just by launching from Earth's surface. No rocket we've ever built can deliver that kind of change. Even nuclear propulsion, which is far more efficient than chemical rockets, would struggle. Gravity assists bypass the problem entirely. The planet does the work. The spacecraft just has to be in the right place at the right time. Pioneer 10 was the proof of concept. Launched in March 1972, it was the first spacecraft to cross the asteroid belt, the first to visit Jupiter, and the first to use a gravity assist to reach escape velocity from the solar system. The Jupiter flyby in December 1973 accelerated Pioneer 10 to about 14 kilometers per second relative to the Sun, fast enough to escape and coast outward forever. The spacecraft continued transmitting data until January 2003, when it was more than 80 astronomical units from the Sun, and the signal finally became too weak to detect. It's still out there, moving at about 12 kilometers per second, carrying a gold plaque with a diagram of a man, a woman, and a map showing Earth's location in the galaxy. The plaque was Carl Sagan's idea, a message in a bottle for anyone or anything that might find the spacecraft millions of years from now. Pioneer 11 followed in April 1973, also visiting Jupiter before swinging past Saturn in September 1979, and then heading out of the solar system. Contact was lost in 1995. Both Pioneer spacecraft proved that gravity assists weren't just theoretical. They worked, they were reliable, and they opened the door to missions that would have been impossible otherwise. Voyager 1 and Voyager 2 expanded on that success, visiting 4 planets instead of 1, and sending back images that redefined how humanity thought about the outer solar system. The Voyagers are still the gold standard for what gravity assists can achieve when everything goes right. They're also a reminder of how rare those opportunities are. The alignment that made the Grand Tour possible won't happen again in our lifetimes. If you want to reach the sun's poles, you don't have the luxury of waiting for a perfect alignment. You have to work with whatever the planets give you. The physics of gravity assists is simple in principle, but complex in execution. It's one thing to say a spacecraft gains velocity by flying past a planet. It's another thing to calculate exactly how much velocity it gains, in exactly what direction, at exactly what time, and then design a trajectory that threads the needle between success and failure. Mission planners use software that simulates trajectories over and over, testing thousands of possible paths, optimizing for fuel efficiency, science return, mission duration, risk. The final trajectory is the result of compromises. Maybe you don't get exactly 90 degrees, but you get 80, and that's close enough. Maybe you don't get the lowest possible flyby altitude, but you get low enough to make the science worthwhile without frying the spacecraft's electronics. Maybe the mission takes 12 years instead of 8, but it arrives and it works. Ulysses was a compromise. 80 degrees instead of 90. A single Jupiter flyby instead of multiple assists. A trajectory that worked within the budget and technology available in the early 90s, and it succeeded. It gave us the first and so far only view of the sun's poles. It proved the concept. It showed that climbing out of the ecliptic was possible, valuable, and repeatable. What it didn't show was whether anyone would actually repeat it. So here's the state of play. Gravity assists are the escape route. They're the way out of the Flatland. Jupiter is the key. Saturn is a backup. The trajectories are calculable, the technology exists, the fuel requirements are manageable, the risks are understood, and yet no mission has been funded to go back. No mission has been designed to finish what Ulysses started. No spacecraft is currently on the way to the sun's poles, and no spacecraft is scheduled to launch there in the next decade. The gap Ulysses opened is still open. The photograph is still missing. The poles remain unexplored. The tools are sitting on the table. The physics is waiting. The planets are there, orbiting the sun, ready to be used as stepping stones the way they've been used for 50 years. All that's missing is the decision to build the mission, fund the launch, and wait for the results. It's not impossible. It's not even especially difficult compared to some of the things we've already done. It just hasn't been a priority, and until it becomes one, the view from 90 degrees above the sun will remain theoretical, a trajectory we know how to fly, a place we know how to reach, a photograph we know how to take, and a blank spot in the archive where that photograph should be. The slingshot is ready. The target is in range. Someone just has to pull the trigger. We've been talking about gravity assists like they're the end of the story. Like Ulysses figured it all out, proved it could be done, and now the only question is whether anyone bothers to do it again. But that's not quite right. Ulysses didn't finish the story. It opened a chapter, and then the book closed. The mission ended in 2009. The spacecraft went silent. And in the 15 years since, no one has gone back. No follow-up mission has launched. No polar orbiter is under construction. No spacecraft is currently on a trajectory that will take it anywhere near the sun's poles. The gap is still there. The photograph is still missing. And the longer we wait, the more the question shifts from how we do it to why we haven't. The answer, as it always is with space exploration, comes down to money and priorities. Building a spacecraft costs billions. Launching it costs hundreds of millions more. Operating it for a decade or two of flight time costs tens of millions per year. You can't fund a mission like that on enthusiasm alone. You need a scientific case strong enough to convince a room full of administrators that this mission, out of dozens of competing proposals, deserves the limited budget available. You need engineers willing to spend years designing systems that won't be tested until long after they've moved on to other projects. You need politicians willing to commit funding that spans multiple election cycles. And you need the public, or at least the fraction of the public that pays attention to space science, to care enough that cancelling the mission would generate backlash. That's a high bar. Most proposed missions don't clear it. The ones that do tend to have a clear hook. Mars missions promise the possibility of finding life. Europa missions promise oceans and maybe life. Missions to the outer planets promise stunning images of alien worlds. A mission to the sun's poles promises better measurements of the solar wind and magnetic field. That's not a bad scientific goal. It's actually a very important scientific goal, but it doesn't capture the imagination the way a photograph of Jupiter's clouds or Saturn's rings does. The sun's poles look more or less like the sun's equator, a sphere of glowing plasma. From a distance, you can't tell the difference. The data is what matters, not the image. And data, as valuable as it is, doesn't sell missions to the public the way images do. So the missions that have been proposed over the years to go back to the sun's poles to finish what Ulysses started have mostly stayed on the drawing board. Studied, analyzed, costed out, and then shelved. Not because they're bad ideas, because they're expensive ideas competing with other expensive ideas, and the other ideas won. Mars rovers win, James Webb wins, Europa Clipper wins, a solar polar orbiter loses, again and again. The pattern holds, and the gap gets wider. But the ideas are still there. Engineers keep refining them, scientists keep advocating for them, and every few years a new proposal surfaces, updated with better technology, more ambitious goals, and a slightly different pitch to make it sound more appealing than the last version. Some of those proposals are modest, small spacecraft, short missions. Do what Ulysses did, but with modern instruments. Others are wildly ambitious. Massive spacecraft, nuclear propulsion, decades-long missions that wouldn't just fly past the poles but orbit them, hovering overhead, mapping the sun in 3 dimensions over multiple solar cycles. Those missions would cost tens of billions of dollars. They'd take decades to build and launch, and they'd produce data that would rewrite textbooks. The scientific return would be extraordinary. The political will to fund them doesn't exist, not yet. Maybe not ever. One of the more realistic proposals that's been floating around for the last decade is called Solar Polar Orbiter. Not to be confused with Solar Orbiter, the European mission that launched in 2020 and is currently working its way up to a 33-degree inclination. Solar Polar Orbiter, with the word polar emphasized, is a concept for a mission that would go all the way, 90 degrees, true polar orbit. The spacecraft would launch toward Jupiter, use a gravity assist to tilt its orbit perpendicular to the ecliptic, and then settle into an elliptical orbit that carries it directly over the Sun's north and south poles every few years. The mission would last at least one full solar cycle, 11 years, so scientists could watch the poles evolve as the Sun's magnetic field flips. Ideally, the mission would last 2 or 3 cycles, build up a dataset large enough to really understand how the polar regions work, how they change, and how they drive the rest of the sun's behavior. The spacecraft would carry a suite of instruments similar to what Ulysses had, but better. Higher resolution cameras, more sensitive magnetometers, spectrographs that could measure the composition of the solar wind down to trace elements, particle detectors that could track cosmic rays streaming in from outside the Heliosphere, and maybe, if the mission got funded at a high enough level, an imaging suite that could actually photograph the sun from above. Not just a spectrograph reading, not just a data stream, an actual picture. The sun's north pole centered in the frame, the solar equator spread out in a circle below it, the corona glowing around the edges, the photograph humanity has never taken, the one that shows the sun as a sphere instead of a disk, the one that proves we finally climbed out of the Flatland. That mission has been studied. Engineers have run the numbers. It's technically feasible. The trajectory works. The instruments exist. The power systems, probably a radioisotope generator like Ulysses used, can keep the spacecraft alive for decades. The communication systems can transmit data back to Earth from 100 astronomical units away if they have to. The radiation shielding can protect the electronics during the Jupiter flyby. Everything checks out, except the cost, and the cost is high. Somewhere in the range of $3 to $5 billion, depending on how ambitious the instrument suite is and how long the mission lasts. That's not out of line for a flagship mission. James Webb cost about $10 billion. Cassini cost about $4 billion when you include the entire mission lifetime. But Webb had images that people wanted to see. Galaxies, nebulae, planets. Cassini had Saturn's rings and Titan's lakes. Solar Polar Orbiter has data. Valuable, irreplaceable data. But data doesn't win budget battles the way images do. The scientific case is strong. Scientists who work on solar physics and heliospheric science have been arguing for a polar mission for decades. They point out that the sun's magnetic field is generated somewhere near or below the surface, and the field lines emerge at the poles in a simpler, more organized pattern than they do at the equator. If you want to understand how the sun's magnetic field works, how it generates the solar cycle, how it drives solar flares and coronal mass ejections, you need to study the poles. You can't reconstruct the full picture from equatorial measurements alone. It's like trying to understand how a car engine works by only looking at the wheels. You're missing the part that makes everything else move. The poles are also where the fast solar wind comes from. Ulysses proved that. The solar wind at the poles is faster, smoother, and more consistent than the wind at the equator. That wind shapes the heliosphere. It determines how far the sun's influence extends, how the heliopause forms, how cosmic rays are deflected. If you want to understand the heliosphere, which is the environment Earth and all the other planets live in, you need to understand the poles. And you can't do that from the ecliptic. You need a spacecraft that's actually there, measuring the wind as it accelerates away from the poles, tracking the magnetic field lines as they stretch out into space, watching how the structure changes over time. And then there's the cosmic ray question. Cosmic rays, high-energy particles from outside the solar system, mostly from supernova explosions, stream into the heliosphere from all directions. But they don't penetrate uniformly. The sun's magnetic field deflects some of them. The solar wind scatters others. The exact amount of deflection depends on the structure of the field and the speed of the wind, and both of those are different at the poles than at the equator. Ulysses found that cosmic rays reach the inner solar system more easily during solar minimum, when the sun's magnetic field is weaker, than during solar maximum. But Ulysses only sampled the poles a few times. A dedicated polar orbiter could measure cosmic rays continuously over multiple solar cycles, building up a dataset that would let scientists model exactly how the heliosphere shields Earth from galactic radiation. That matters for understanding space weather. It matters for planning crewed missions to Mars and beyond. It matters for understanding how the radiation environment on Earth changes over geological timescales. So the science is there, the case is solid. The problem is convincing the people who control the budget that this science is more important than whatever else is competing for the same money. And right now, there are a lot of things competing. Mars sample return. A mission to return rocks from Mars to Earth for detailed analysis. That's expensive. Europa Clipper just launched, and it's going to cost over $4 billion by the time the mission ends. A potential mission to Enceladus, Saturn's tiny moon with geysers erupting from its south pole, is being studied. A mission to Neptune or Uranus, the ice giants that haven't been visited since Voyager 2 flew past in the late 1980s. All of those missions have constituencies, all of them have scientists advocating hard, and the budget is finite. Solar Polar Orbiter is in the queue. It's been in the queue for years, but it keeps getting bumped. There's another version of the mission that's even more ambitious. Instead of just flying over the sun's poles, this version would send a spacecraft out of the solar system entirely, far enough that it could turn around and photograph the solar system from above, not from 100 astronomical units, from farther, thousands of astronomical units. Far enough that the sun becomes a bright star, and the planets, if you squint, might be faint dots scattered around it. Far enough that the heliosphere, that bubble of solar wind stretching 100 astronomical units in every direction, looks like a bubble, a glowing sphere of plasma pushing against the dark. That mission doesn't have a formal name. It's been called the Interstellar Heliosphere Probe in some proposals, the Solar System Portrait Mission in others. The basic idea is simple. Launch a spacecraft on a trajectory that takes it out of the ecliptic plane using a Jupiter gravity assist, just like Ulysses. But instead of stopping at the sun's poles, keep going, climb higher, use a second gravity assist, maybe from Saturn, to add more velocity and tilt the trajectory even steeper. Head out into interstellar space on a path that's nearly perpendicular to the ecliptic plane. Fly for decades. And when the spacecraft is far enough out, maybe 1,000 astronomical units, maybe more, turn the camera around and take the picture. The solar system from above. The sun at the center. The planets too faint to see individually, but their orbits implied by the faint glow of zodiacal dust in the ecliptic plane. The heliosphere visible as a faint halo around the sun, glowing in ultraviolet or X-rays depending on what instruments you're using. The photograph that shows the solar system not as a collection of individual worlds, but as a single structure, a system, a sphere of influence carved out of the galaxy. The engineering challenges for a mission like that are enormous. The spacecraft would need to survive for 50 years or more. Voyager 1 took 35 years to reach 120 astronomical units. A spacecraft aiming for 1,000 astronomical units would take centuries unless you could accelerate it significantly faster than Voyager. And faster means more fuel, which means more mass, which means a bigger rocket, which means more cost. You could use nuclear propulsion, ion drives powered by a small nuclear reactor. That would be more efficient than chemical rockets, but it would also be more complex, more expensive, and politically harder to launch. Nuclear anything in space makes people nervous, even though radioisotope generators like the ones on Voyager and Ulysses use plutonium and have been flying safely for decades. Or you could use solar sails, thin reflective sheets that catch sunlight and use the pressure of photons to accelerate. Solar sails are extremely lightweight, which means you don't need much fuel to get them moving, but they're slow. Accelerating a solar sail to the speeds needed to reach 1,000 astronomical units in a reasonable time frame would require a sail the size of a football field and decades of patient acceleration. By the time the spacecraft reached its destination, the people who built it would be long dead. The scientists who proposed the mission would be long dead. The entire field of solar physics might have moved on to other questions. That's a hard sell. There's one other option that's been seriously proposed: a laser-pushed sail. Instead of using sunlight, you build an enormous laser array on Earth or in orbit around Earth, and you aim it at the spacecraft. The laser beam hits the sail, transferring momentum, and accelerates the spacecraft far faster than sunlight alone ever could. Breakthrough Starshot, a privately funded initiative announced in 2016, is exploring this concept for sending tiny probes to Alpha Centauri, the nearest star system, 4.3 light-years away. The idea is to accelerate postage stamp-sized spacecraft to 20% the speed of light, fast enough to reach Alpha Centauri in about 20 years. If that technology works, and it's a big if, you could use a scaled-down version to send a much larger spacecraft out of the ecliptic plane at high speed, reach 1,000 astronomical units in a decade or two instead of a century, take the photograph while the mission team is still alive to see it. But laser-pushed sails are speculative. The technology isn't proven. The lasers required would be incredibly powerful, possibly dangerous and expensive to build. And even if you solved all the technical problems, you'd still need to convince someone to fund it. That's the recurring theme. The ideas exist. The technology, or at least the path to the technology, exists. What doesn't exist is the funding, the political will, the public excitement that turns a concept into a mission. Meanwhile, the modest proposals keep coming. Not 1,000 astronomical unit probes, not laser sails, just updated versions of Ulysses, small spacecraft, proven technology, a single Jupiter flyby, 80 or 90-degree inclination, a decade of observations, then move on. Those missions are affordable, $1 billion, maybe $2. That's cheap by flagship mission standards, and the science return would be immediate. You'd get data from the poles within a few years of launch. You'd watch the solar cycle unfold from a vantage point no one has had since Ulysses went silent. You'd measure the magnetic field, the solar wind, the cosmic rays, all the things Ulysses measured, but with instruments 30 years more advanced. Better sensitivity, higher resolution, more data. The case practically writes itself. And yet those missions don't get funded either. Not because they're bad, because they're not flashy. They don't promise life on other worlds. They don't promise stunning images. They promise better models of the sun's magnetic field and improved understanding of space weather. That's important. It's legitimately important. But it's not the kind of important that generates headlines or excites the public or convinces politicians that this is the mission we absolutely must fund right now. So the proposals sit, they get reviewed, they get rated highly by scientific panels, and then they get deferred, maybe next decade, maybe the decade after, maybe never. There's an irony here. The sun is the most important object in the solar system. It's the source of almost all the energy that drives weather, climate, ocean currents, photosynthesis, everything that makes Earth habitable. It's the anchor that holds the solar system together. It's the shield that protects us from galactic cosmic rays. And we've barely studied it outside the ecliptic plane. We've sent dozens of missions to Mars, a cold, dead rock with no magnetic field and an atmosphere so thin you can almost ignore it. We've sent multiple missions to Jupiter, Saturn, and their moons. We've sent probes to comets, to asteroids, to the edge of the solar system. But we've sent exactly one mission to the sun's poles, and it ended 15 years ago. That's not a balanced exploration strategy, that's a gap. A blind spot, a piece of the solar system we've decided, implicitly, isn't worth prioritizing. The argument you hear from mission planners is that the sun is being studied. Solar Orbiter is climbing out of the ecliptic right now. It'll reach 33 degrees by the end of its nominal mission. Parker Solar Probe is diving closer to the sun than any spacecraft ever has, skimming through the corona, measuring the solar wind at its source. Those missions are doing good science. They're answering important questions, but they're not going to the poles. Solar Orbiter is getting closer, but 33 degrees is not 90. Parker is getting closer to the sun, but it's staying in the ecliptic. The poles remain out of reach, and the longer we wait, the more we risk missing things. The sun changes. The solar cycle is 11 years. If you wait another decade to launch a polar mission, you miss an entire cycle. If you wait 2 decades, you miss 2 cycles. The data Ulysses collected is now 15 years old. The sun has gone through more than a full cycle since then. The magnetic field has flipped. The solar wind has waxed and waned. The cosmic ray environment has shifted, and no one was watching from above. No spacecraft was there to measure it. The data is gone. You can't go back in time and collect it. You can only move forward and hope the next cycle gets observed. There's also the question of what we don't know we're missing. Ulysses found surprises, the fast solar wind at the poles, the oxygen in the solar atmosphere at high latitudes, the unexpectedly high flux of interstellar dust streaming into the solar system. None of those things were predicted. They were discovered because Ulysses was there to measure them. What else is happening at the poles that we don't know about because we haven't looked? What structures are forming in the corona above the poles that we can't see from the ecliptic? What patterns are emerging in the magnetic field that only make sense when you view them from above? We won't know until we go back, and we won't go back until someone funds the mission. The photograph is part of the pitch, but it's not the whole pitch. The photograph, the overhead view of the sun, the image that shows the poles centered in the frame with the equator spread out below, that's a visual. It's compelling. It's the kind of thing that could end up on the cover of a textbook or in a museum exhibit. But it's not the science. The science is the data, the measurements, the magnetic field readings, the particle counts, the spectra, the time series observations that build up over months and years into a dataset rich enough to test models and answer questions. The photograph is a single frame, the dataset is a movie, and scientists care about the movie, but the public cares about the photograph, and the public indirectly controls the budget. If a mission can generate public excitement, if it can produce images that people want to see and share and talk about, it has a much better chance of getting funded and staying funded. That's why Mars rovers have cameras that take color photographs of the landscape. The science could be done with black and white images, or even just with spectrometers analyzing the soil. But the color photographs matter because they make Mars feel real. They turn data into a place, and places are easier to care about than data sets. A photograph of the sun from above could do the same thing. It would turn the sun from a glowing disk in the sky into a sphere, a world, an object with geometry and structure that you can see and understand. It would show people something they've never seen before, a perspective that's genuinely new, and that novelty matters. It's the difference between reading about a place and seeing it. Both are valuable, but the seeing sticks with you in a way the reading doesn't. So the mission concepts keep including imaging, high-resolution cameras, wide-angle cameras, ultraviolet images that can see the corona, X-ray images that can see the hottest structures near the poles, magnetographs that can map the magnetic field and overlay it on the images, showing how the field lines thread through the atmosphere. The engineers know the photograph matters. The scientists know the photograph matters. What they're waiting for is someone in a position of authority to agree that it matters enough to actually fund the mission. The technological barriers are real but not insurmountable. Propulsion is the hardest part. Getting a spacecraft to 90 degrees inclination requires a close Jupiter flyby or multiple gravity assists or some combination of both. Chemical rockets can do it. Nuclear rockets could do it faster and more efficiently. Solar sails could do it slowly. Laser-pushed sails could do it very fast if the technology matures. The options exist. Picking one depends on the mission timeline, the budget and the risk tolerance. Power is the second hardest part. Solar panels don't work well when you're far from the sun or spending most of your time above or below the ecliptic, where the sun's angle is steep. Radioisotope generators work, but they're expensive and the supply of plutonium-238 is limited. NASA only produces a few kilograms per year, and multiple missions are competing for it. A polar mission would need a generator large enough to power instruments for a decade or more. That's doable, but it's not cheap. Communications are challenging but solvable. A spacecraft 100 astronomical units from Earth, the distance Ulysses reached at aphelion, experiences a light travel time of about 14 hours. That means any signal you send takes 14 hours to arrive, and any response takes another 14 hours to come back. You can't operate the spacecraft in real time. You send commands, wait, and hope they execute correctly. Ulysses managed it. Voyager manages it from even farther out. The distance is not the problem. The problem is keeping the antenna pointed at Earth when the spacecraft is tumbling or spinning or maneuvering. That requires precise attitude control, reaction wheels or thrusters, and enough power to keep the systems alive. All of that adds mass, which adds cost. Radiation is the other major challenge. The Jupiter flyby exposes the spacecraft to intense radiation from Jupiter's magnetosphere. The closer you fly, the worse it gets. Ulysses was shielded, but not heavily. It survived the flyby but took damage. A modern mission would need better shielding, which means more mass, which again adds cost. Once the spacecraft is past Jupiter and climbing out of the ecliptic, the radiation environment gets calmer. The solar wind is less intense at high latitudes. Cosmic rays are more of a concern, but shielding against cosmic rays is different from shielding against trapped radiation belts. You need different materials, different geometries. It's all solvable. It just takes engineering time and money. The mission would also need to survive thermal extremes. Above the poles, the sun's heating is more direct in some sense because you're looking straight down at it, but the spacecraft's distance from the sun would vary as it moved through its elliptical orbit. At perihelion close approach, the heating could be intense. At aphelion, far from the sun, the spacecraft would get cold. Managing those swings requires thermal control systems, heaters, radiators, insulation. Ulysses had all of that. It worked for nearly 2 decades. The technology is proven. It just needs to be updated for modern instruments. So the barriers are high but not insurmountable. The trajectory is hard but not impossible. The technology is expensive but not unavailable. What's missing is the decision to actually build the mission. And that decision ultimately comes down to priorities. What does humanity want to know? What are we willing to spend to find out? And whose job is it to decide? NASA has a process for this. Every 10 years, the planetary science community gets together and writes a document called the Decadal Survey. It's a thick report, hundreds of pages, that lists the most important scientific questions in planetary science and recommends which missions should be funded to answer them. The survey is written by scientists, reviewed by committees, and presented to NASA and Congress as a roadmap for the next decade. The missions that make it into the survey have a much better chance of getting funded. The missions that don't mostly disappear. A solar polar orbiter has appeared in multiple decadal surveys. It's been recommended. It's been rated highly. But it's never been rated highly enough to jump to the front of the line. There's always something else that seems more urgent. Mars sample return. A Europa lander. A mission to an ice giant. The polar orbiter gets mentioned, gets praised, and then gets deferred. Maybe next decade. The pattern has held for 20 years. There's no reason to think it won't hold for another 20. But the scientific case is not going away. The sun's poles are still unexplored. The heliosphere is still unmapped in 3 dimensions. The cosmic ray environment is still not fully understood. The questions are still there. And eventually someone will decide those questions are important enough to fund a mission to answer them. When that happens, the technology will be ready, the trajectories will be calculated, the instruments will be designed, and the mission will launch. It might be 10 years from now, it might be 30, but it will happen, because the gaps don't stay open forever. Science has a way of circling back to the questions that didn't get answered the first time. When it does happen, when the spacecraft finally climbs out of the ecliptic and settles into a polar orbit around the sun, when the instruments turn on and the data starts streaming back, when the camera points downward and captures that first overhead image of the sun's north pole, the photograph will be historic, not because it's beautiful, though it might be, not because it's surprising, though it could be, because it's new, a perspective humanity has never had, a view that changes how we think about the sun, the solar system, and our place in both. That photograph will be worth the wait. The question is how long we're willing to wait before we decide it's worth the cost. We've been circling this from the beginning. The ecliptic trap, the unseen poles, the photograph we've never taken. But if you step back from the details, the trajectories, the gravity assists, the mission proposals that keep getting shelved, what you're really looking at is a story about perspective, about how the angle you see something from shapes what you think it is, and about how hard it is, how expensive it is, how much effort it takes to step outside your own frame of reference and look at the thing you thought you understood from a direction you've never tried. That's not just true for the sun, it's true for everything. Every field of science, every branch of knowledge, every attempt to understand something complicated has this same problem baked into it. You see what you're looking at from where you're standing, and where you're standing determines what's visible and what's hidden. Change your position and the hidden thing might become obvious. The thing that seemed obvious might vanish. The shape you thought was a circle might turn out to be a sphere, or a cylinder, or something you don't have a name for because you've never seen it whole. We started with the ecliptic, that flat plane where all the planets orbit, where every mission we've ever launched has stayed because that's where the targets are and that's where the fuel budget says you have to go. It made sense. It still makes sense. The planets are there. The science is there. You can't blame mission planners for following the most efficient path to the most interesting destinations. But efficiency has a cost. The cost is that you end up seeing everything from the same angle. You build a map of the solar system from inside a single narrow slice, and after a while, you start thinking that slice is the whole picture. It's not. It never was. But it's the only picture you have, so it becomes the picture. Ulysses broke out, 80 degrees above the ecliptic. Not 90, but close. Close enough to see the sun's poles, to measure the fast solar wind streaming away from them, to watch the magnetic field flip polarity over the course of a solar cycle. It was the first time anyone had looked at the sun from outside the plane, and what it saw didn't match the models. The solar wind was faster than predicted. The magnetic field was weaker. Cosmic rays were streaming in from directions that shouldn't have been open. Every measurement Ulysses sent back was a reminder that the Sun, the most studied object in the solar system, the star we've been staring at for all of recorded history, still had surprises left, still had structure we couldn't see from the ecliptic, still had dynamics we didn't understand because we'd never bothered to climb high enough to look. And then Ulysses went silent. The plutonium decayed, the power dropped, the fuel lines froze. The spacecraft is still up there, orbiting the Sun every 6 years, passing over the poles with dead instruments and a silent transmitter, a monument to a question we asked once and then stopped asking. 15 years have passed since Ulysses shut down. The Sun has gone through more than a full cycle. The magnetic field has flipped again. The solar wind has waxed and waned. The poles have been active, dynamic, changing, doing whatever it is they do when no one is watching. And no one has been watching. No spacecraft has gone back. No mission has launched. The gap Ulysses opened is still open, wider now than it was, and the longer it stays open, the more it starts to feel less like a gap and more like a choice, a decision, implicit but real, that the view from the poles isn't worth the cost of going back. That decision isn't irrational. Space exploration runs on limited budgets. Every mission that gets funded means a dozen others don't. The proposals that win are the ones with the most compelling science, the clearest objectives, the best chance of producing results that justify the investment. A solar polar orbiter has good science, it has clear objectives, but it doesn't have the kind of result that generates headlines. It doesn't promise life on other worlds. It doesn't promise stunning images of alien landscapes. It promises data, better models of the Sun's magnetic field, improved understanding of the solar wind, more accurate predictions of space weather. Those are valuable things, they matter, but they don't capture the public imagination the way a rover on Mars does, or a probe diving through the geysers of Enceladus, or a telescope spotting galaxies from the first billion years after the Big Bang. So the polar orbiter stays on the drawing board. It gets studied, costed, recommended, and then it gets deferred. But here's the thing about perspective. You don't always know what you're missing until you see it. Ulysses didn't set out to overturn the models. It set out to test them, to measure what the models predicted and confirm that the predictions were right. Instead, it found that the predictions were wrong. Not catastrophically wrong, not break all the textbooks wrong, just wrong enough that every solar physicist who looked at the data had to go back and revise their assumptions. The fast solar wind, the weak polar magnetic field, the cosmic ray flux, none of those were anticipated. They were discovered, and discoveries, by definition, are things you didn't know to look for. You can't predict what you'll find when you finally see something from a new angle. You just know that the angle matters. The photograph we've never taken, the view from 90 degrees above the Sun, is a symbol of that. It's not that the photograph itself would revolutionize solar physics. The data is what matters, the measurements, the time series observations that build up over months and years into a dataset rich enough to answer questions. But the photograph represents something. It represents the moment when the Sun stops being a disk in the sky and becomes a sphere, a world, an object you can see whole, in 3 dimensions from outside. It's the difference between looking at a map and looking at a globe. Both show you the same information technically, but the globe shows you the shape, the way the pieces connect, the way the structure fits together, and that matters. There's a parallel here to almost every major breakthrough in the history of science. Perspective changes everything. When astronomers figured out that Earth wasn't the center of the solar system, it wasn't because they discovered a new planet or saw something in the sky that no one had seen before. It was because they changed their perspective. They stopped assuming Earth was stationary and started imagining what the sky would look like if Earth were moving. Suddenly, the weird looping paths of the planets, the retrograde motions that had baffled astronomers for centuries, made sense. The planets weren't actually looping, they were just moving in circles, and Earth was moving too, and the combination of those motions created an illusion. Change your frame of reference and the illusion disappears. When geologists figured out that continents move, it wasn't because they found new rocks or discovered new fossils. It was because they looked at a map and noticed that the coastlines of Africa and South America fit together like puzzle pieces. That observation had been staring people in the face for centuries. Literally anyone with a globe could have noticed it. But no one took it seriously until Alfred Wegener proposed continental drift in the early 1900s. And even then, most geologists dismissed the idea because they couldn't imagine a mechanism that would move something as massive as a continent. It took another 50 years and the discovery of seafloor spreading before the perspective shift stuck. Now we call it plate tectonics, and it's the foundation of geology. The continents were always moving. We just couldn't see it because we were standing on them. When doctors figured out that bacteria cause disease, it wasn't because disease suddenly became more common or symptoms suddenly became clearer. It was because someone invented the microscope and looked at a drop of water from a different angle. An angle small enough to see the microorganisms swimming around in it. Before that, disease was blamed on bad air, imbalanced humors, divine punishment, all kinds of explanations that made sense within the framework people were using. The bacteria were always there. We just couldn't see them because we didn't have the tool to change our perspective. Once we did, medicine transformed. Sanitation, antibiotics, vaccines, all of it followed from the realization that invisible living things were causing the symptoms we'd been observing for millennia. Perspective is not optional. It's not a luxury you add after you've figured out the basics. It's the thing that lets you figure out the basics in the first place. And the hardest perspectives to gain are the ones that require you to step outside the system entirely and look back. To stop being embedded in the thing you're studying and become an external observer. That's what the solar polar mission would do. It would take us out of the ecliptic, the plane we've been embedded in for all of human history, and let us look back at the sun from outside. Not as a participant in the solar system's motion, but as an observer watching the system from a distance. That shift, from inside to outside, is profound. It's the same shift that happened when astronauts went to the moon and photographed Earth from space. The famous Earthrise photo, the blue marble. Those images didn't reveal new continents or oceans. Everyone already knew the continents and oceans were there. But seeing Earth from outside, as a single fragile sphere hanging in the black, changed how people thought about the planet. It made the atmosphere look thin. It made the borders look arbitrary. It made the whole thing look smaller and more vulnerable than it seemed when you were standing on the ground looking up. That's what perspective does. It changes the scale. It changes the context. It changes what seems important. The sun is not a disk, it's a sphere. We know that intellectually, we've known it for centuries, but we've never seen it as a sphere from outside the ecliptic plane. Every photograph, every observation, every model, all of it comes from the side view, the equatorial view. The view you get when you're standing on one of the planets orbiting in the same flat plane the sun's equator defines. From that view, the sun looks like a circle, a flat glowing circle with some dark spots and some bright patches, but fundamentally flat, two-dimensional. You can infer the third dimension. You can measure it, calculate it, model it, but you can't see it. Not really. Not the way you'd see it if you climbed 90 degrees out of the plane and looked straight down at the pole. From there, the sun wouldn't look flat. It would look round, curved, a ball of plasma rotating beneath you, with structure radiating outward in all directions. The corona wouldn't be a halo around the edge. It would be a glow above the surface, stretching up toward you, three-dimensional and alive. The magnetic field lines wouldn't be abstract curves on a diagram. They'd be real structures threading through space, visible in the way the plasma follows them, shapes itself around them, flows along them as it escapes into the solar wind. That's the view we're missing. And it's not just a solar physics problem, it's a reminder that perspective is always incomplete. You can study something for centuries, build models that predict its behavior with incredible accuracy, write equations that describe every detail, and still miss something fundamental because you've only ever looked at it from one direction. The sun has been studied longer and more intensely than almost any other object in the universe. We've pointed telescopes at it, we've sent spacecraft to orbit it. We've measured its spectrum, its magnetic field, its oscillations, its wind. We've modeled the nuclear reactions in its core. We've predicted solar flares and coronal mass ejections. We've mapped the heliosphere all the way out to the heliopause, and yet we've never looked at it from above. That one missing angle is enough to leave entire questions unanswered. How does the magnetic field behave at the poles? How does the solar wind accelerate there? How do cosmic rays penetrate the heliosphere from high latitudes? We have models, we have guesses, but we don't have data. And in science, data is the only thing that matters. The model doesn't tell you what's true. The data tells you what's true, and the model is just your best attempt to explain it. If you're missing data from an entire angle, your model is incomplete. It might be right, it might be close, but it's incomplete. The philosophical weight of this is heavier than it seems at first. We live inside the solar system, not just in the sense that Earth is one of the planets, but in the sense that our entire frame of reference is shaped by being here. We see the sun from Earth's orbit. We see the planets from Earth's latitude. We see the galaxy edge on because we're embedded in its disk. Every observation we make, every measurement we take, every photograph we capture is taken from inside the system. We are not external observers, we are participants, and participants have biases. Not intentional biases, not biases that come from wanting a particular result. Geometric biases, the bias of being in one place and not another, of seeing one angle and not the rest, of assuming that what's visible is all there is because the invisible hasn't been accessible. Climbing out of the ecliptic to see the sun's poles is in a way an attempt to escape that bias, to stop being a planet orbiting in the plane and become something else, an observer, a camera floating above the system, looking down, seeing the whole structure instead of just the slice. It's a small step in the grand scheme of things, 90 degrees of inclination, 100 astronomical units above the plane, barely a rounding error compared to the scale of the galaxy, but it's enough to shift the frame of reference, enough to see something we've never seen, enough to remind us that perspective is not fixed, it's a choice that costs fuel and money and time, but a choice nonetheless. And here's the uncomfortable part. We haven't made that choice. Not since Ulysses. We've chosen Mars instead. We've chosen Europa. We've chosen the outer planets, the asteroids, the comets, the Kuiper belt. All of those are valid choices. All of those have produced extraordinary science. But the sun's poles are still sitting there unobserved, waiting for someone to decide they matter enough. And the longer we wait, the more the gap in our understanding grows. The solar cycle doesn't pause. The sun doesn't stop changing just because we're not watching. Every year we delay is another year of data we'll never get back. Another cycle we'll only understand from the equator. Another opportunity to see the sun whole that we've chosen to pass up. There's a lesson in that about priorities, about what we value and what we don't. Space exploration at its best is about pushing boundaries, about going to places no one has been, seeing things no one has seen, asking questions no one has answered. But it's also a mirror. It reflects back what we think is important, what we're willing to spend money on, what we're willing to wait for, what we're willing to risk. And right now, the reflection shows that we value destinations over perspectives. We value worlds we can land on over angles we can look from. We value the possibility of life, even if it's microbial life frozen in Martian soil, over the certainty of better understanding the star that makes all life possible. That's not wrong. It's a choice. But it's worth recognizing it as a choice and asking whether it's the right one. The human drive to explore is powerful. It's one of the things that makes us what we are. We've crossed oceans, climbed mountains, reached the poles of our own planet, sent robots to other worlds. We've built telescopes that can see galaxies billions of light years away. We've measured the cosmic microwave background, the faint glow left over from the Big Bang itself. We've detected gravitational waves from colliding black holes. We've photographed the shadow of a black hole's event horizon. All of that is extraordinary. All of that required pushing past the limits of what seemed possible and finding ways to see things that were previously invisible. But that drive, that need to see what's over the next hill, doesn't always point in the obvious directions. Sometimes the most important thing to see isn't far away. It's close. It's just hidden by the angle you've been looking from. The solar system is our island, the one patch of space we can actually reach with current technology, the one region where we can send spacecraft, take measurements, collect samples, and bring them home. Beyond the solar system, we're observers. We can look, we can listen, but we can't touch, we can't land, we can't send a probe to another star and get data back in a human lifetime. The solar system is the laboratory. It's where we test ideas about how planets form, how atmospheres evolve, how magnetic fields work, how radiation interacts with matter. It's where we learn the rules that apply everywhere else. And if we don't understand our own star, the one we live next to, the one that dominates everything about the environment we exist in, then we're missing something foundational. Something that will show up as a gap in every other model we build, every other system we try to understand. The view from 90 degrees above the sun would close part of that gap, not all of it. Science doesn't work that way. You don't take one measurement and suddenly understand everything, but it would add a data point we don't have, a perspective we've never had, a piece of the puzzle that's been missing since we started studying the sun in the first place. And maybe, just maybe, it would reveal something unexpected, something we didn't predict, something that forces us to go back and rethink not just the sun, but the entire heliosphere, the way the solar wind shapes interplanetary space, the way the magnetic field shields us from cosmic rays, the way the sun breathes in and out over its 11-year cycle. Ulysses found unexpected things. There's no reason to think a mission to the poles wouldn't find more. But even if it doesn't, even if every measurement comes back exactly as the models predict, even if the view from above confirms everything we already think we know, the photograph itself would still matter, because it's not just about the data, it's about the perspective. It's about proving to ourselves that we can step outside the Flatland, that we can climb out of the plane we've been trapped in for all of recorded history, and see the system we live in from an angle we've never tried. That act, that choice to go there just to see what it looks like, is worth something. It's a statement about what kind of species we want to be. Do we want to be the species that stays in the ecliptic because it's cheaper and easier? Or do we want to be the species that climbs out even when it's hard, even when it's expensive, because the view from outside is part of understanding where we are. That's not a question with an obvious answer. Both choices are defensible. Both have costs and benefits, but it's worth asking. Because the longer we go without asking it, the longer we go without funding the mission, the longer we go without pointing a camera 90 degrees above the sun and taking the photograph, the more it starts to feel like we've already made the choice by default. We've chosen to stay in the Flatland, not because we couldn't leave, because we decided it wasn't worth the effort. And maybe that's fine. Maybe the data from the Ecliptic is good enough. Maybe the models are accurate enough. Maybe the questions that would be answered by a polar mission aren't urgent enough to justify the cost. But if that's the decision, it should be a conscious one, not something that happens because the mission keeps getting deferred, keeps sliding down the priority list, keeps losing out to other proposals. It should be a choice we make openly, with full awareness of what we're giving up. The photograph, the data, the perspective, the chance to see the sun whole. Science is a process of narrowing uncertainty. You start with a question, you design an experiment or an observation that might answer it. You collect data, you refine the models, you ask the next question, repeat indefinitely. Every step forward reduces the uncertainty a little bit, makes the picture a little clearer, brings you a little closer to understanding. But the process only works if you're willing to look at the system from multiple angles. If you only ever observe from one direction, you're not narrowing uncertainty, you're just confirming what you can already see. The uncertainty about everything else stays exactly where it is. The sun's poles are that uncertainty. They're the part of the picture we haven't narrowed yet because we've only looked once, briefly, from an angle that wasn't quite perpendicular. The models fill in the gaps. They extrapolate from the equator to the poles. They assume the physics is the same everywhere. And maybe it is. But assumptions are not data. And until we go back, until we measure it again, until we map the poles with modern instruments from a true polar orbit, the uncertainty stays. The power of perspective is that it turns assumptions into measurements. It turns models into tests. It turns the thing you thought you understood into something you actually understand. And it does that by forcing you to look at the system from a direction you weren't looking before. That's the value of the photograph we've never taken, not the image itself, the act of going there to take it, the decision to prioritize the missing angle, the recognition that perspective is not a luxury but a necessity. Cosmic knowledge is not static, it unfolds. Every generation of astronomers, every new instrument, every mission that goes farther or looks deeper or climbs higher, adds another piece. The story is never finished. There's always another question, another gap, another direction no one has looked yet. The sun's poles are one of those directions, a gap in plain sight, a direction we know how to reach but haven't committed to reaching. And as long as that gap stays open, the story of the solar system remains incomplete. Not wrong, not catastrophically flawed, just incomplete, missing a chapter, missing a perspective, missing the view from above. The chapter can be written, the technology exists, the trajectories are mapped, the instruments are ready. All that's missing is the mission, the funding, the political will, the recognition that this gap matters enough to close. And when that recognition finally comes, when someone decides the sun's poles are worth going back to, when the spacecraft launches and climbs out of the ecliptic and settles into its orbit, when the camera points downward and captures that first true overhead view of the sun's north pole, the photograph will arrive, not as a surprise, as a confirmation. A proof that the thing we've been imagining for decades is real, that the sun is a sphere, not a disk, that the poles exist, that they're different, that they matter, that perspective is not optional, And maybe that photograph will be enough. Maybe it'll be the image that finally makes people understand why the angle matters, why stepping outside the flatland is worth the cost, why seeing the sun whole changes something fundamental about how we think about where we are. Or maybe it won't. Maybe it'll be just another data point, filed away in archives, cited in papers, referenced in textbooks, but not remembered the way Earthrise or the pale blue dot are remembered. Either way, it'll be there. The first true photograph of the sun from above, the first view from 90 degrees, the first proof that we climbed out, looked back, and saw the thing we thought we knew from an angle we'd never tried. That's worth doing. Not because it's flashy, not because it promises discoveries that will make headlines, because it's the right angle, the missing angle, the one that closes the gap. The solar system is our home. The sun is its anchor. And we've spent our entire existence looking at that anchor from the side, from the equator, from inside the plane. It's time to climb out, not someday, not eventually, soon, while the tools still work, while the knowledge is still fresh, while the scientists who studied Ulysses's data are still around to interpret the new data, while the gap is still open and the question is still unanswered. The view from above is waiting, the trajectory is plotted, the photograph is possible. All we have to do is decide it's worth taking. That's the lesson, that's the reflection, that's the hidden view. Not a place we can't reach, a place we haven't chosen to go, and the choice, as always, is ours. So here we are, standing on a planet that orbits a star we've studied for centuries, watched with every instrument we've ever built, mapped in wavelengths from radio to gamma ray, sent spacecraft to touch, and yet never once looked at from directly above. Not because we couldn't, because we chose not to, because the ecliptic was good enough, because the planets were there, because the missions that stayed in the plane were cheaper, faster, easier to sell. And for decades that logic held. It made sense. It still makes sense. Until you realize what it cost. Ulysses proved the view from above was different. Faster solar wind, weaker magnetic field, cosmic rays streaming in from directions that shouldn't have been open. Every measurement it sent back was a reminder that the sun, the object we thought we understood better than anything else in the cosmos, still had structure we couldn't see from the side, still had dynamics we didn't predict because we'd never climbed high enough to watch them unfold. And then Ulysses went silent, and no one went back. 15 years, an entire solar cycle, the magnetic field flipped, the poles evolved, and no one was watching. The photograph is still out there, 90 degrees above the sun, looking straight down at the North Pole, the heliosphere glowing beneath you, the solar wind streaming outward in every direction. The one view that would show the sun not as a disk but as a sphere, not as a flat glowing circle in the sky but as the three-dimensional object it actually is. That photograph is possible, the trajectory exists, the technology works. All that's missing is the will. And maybe that's the real question.